part of the gravitational wave was seen, and that made a huge splash in the whole world. But in the same year, a somewhat little minor event got slightly overshadowed probably by the big event of the gravitational waves, was the first detection of high energy neutrino coming from an astrophysical source, and in correlation with very high energy gamma rays and very high energy gamma rays from that same source. So, and that would be the major part of what I would discuss today, and then also certain follow-ups of that. So what astronomers normally do is that they send out telegrams when something interesting happens, when they see something interesting happening. So these are kind of astronomers' telegram, which are just short bursts of information so that other telescopes can react to it within a very short amount of time. So that's the first two telegrams that came out before even when IceCube actually sent out an alert that they have seen a neutrino of a very high energy, and we'll come to all that in the next slides. Fermilab, which is a gamma ray telescope at medium energies operating at few 100 MeV to few GeVs or few tens of GeVs, detected an increased gamma ray activity from a certain blazar, and I'll come to again to all of these, located within the IceCube error region. And a few days later, there was very high energy gamma rays detected by MAGIC from the direction consistent with this IceCube neutrino. So that would be the main part of the talk that started the multi-messenger field using neutrinos and photons. And the primary motivation to do all of that is to look for sources of cosmic rays and to understand the origin of cosmic rays. So most of it I would kind of stick to neutrinos and gamma rays, but I would also show you at some part of the talk that even at lower energies, optical and X-rays are also very important in understanding these objects. So you already know that the origin of cosmic rays cannot be done only using just charged particle astronomy, simply because these cosmic rays get deflected in the magnetic field and then they lose their apparent source direction. However, if there is matter around these sources, they would emit gamma rays or neutrinos, and using gamma rays and neutrinos, you could actually point back to the sources. So what is important is spatial and temporal correlations between neutrinos and gamma rays can trace cosmic ray acceleration sites. However, you could argue that you could have done this only with gamma rays. That is what I started doing several years ago as a PhD student and a postdoc. And there you would have to, we were trying to distinguish between two different types of acceleration mechanisms that you would see. One is the leptonic acceleration, where there would be electrons in the magnetic field. They would produce synchrotron radiation that would produce the first part of the spectrum. And then those synchrotron photons will be upscattered to TeV gamma rays through an inverse Compton effect by the same set of electrons that are present in the system. And there you would see this inverse Compton spectrum in the high energy gamma rays. And then there would also could be hadronic acceleration, where protons would interact with matter, produce pi zeros, and then pi plus and pi minus. The neutral pions would decay into TeV gamma rays, and then they would have certain distinct spectral shape. So one thought that at that time, that if you had data all over the spectral energy, what you call the spectral energy distribution, you should be able to distinguish between the two acceleration mechanisms. It turned out that this is just a cartoon, and the life is much more complicated than that, because there would be also lower energy cascades which would modify all the spectrum, and then the distinguishability is not that apparent. Hence came the neutrinos, so because they start to become then the smoking guns for hadronic accelerators. I don't need to talk too much about IceCube detector. Most of you again know that it's a kilometer cube detector in ice in the South Pole, where they have these digital optical module systems, many thousands of them deployed in ice down to almost 2.5 kilometers from the surface of the ice level. At the top of the ice, they have an air shower array called the IceTop. And so IceCube has been deployed. All these 86 strings and all these digital modules have been deployed over several years. And by 2011-12, they completed the whole array and has been taking data since then. Now, So what one does is that a neutrino infrequently would interact in the ice and then produce a nuclear reaction and then would produce muons. And these muons can travel kilometers in ice, and they produce Cherenkov light as they move with speeds greater than the speed of light in that medium. And these optical sensors catch and map this light. And from that, you get an idea of the energy, you get an idea of the direction. Once you get an idea of the energy and the direction, you can start to think about doing astronomy with it. Okay, so quite early, even before IceCube, when the smaller detector called the Amanda was in place, we had started to think about doing these neutrino, what we call TO is a target of opportunity program. So for example, if you see at least a very energetic neutrino or a cluster of neutrinos coming from a certain direction in sky, you would send triggers to electromagnetic telescopes like these gamma ray telescopes like MAGIC, or the high energy gamma ray telescopes, which are ground-based ones. So we started developing this NTO program way back in 2007. The first alerts were sent around that time. At that time, we were calculating what would be the kind of alert rates, what would be the false alarm rates, and all that. And then this was well tested by 2010, and then they were put in place. However, IceCube had not seen many neutrinos at that time, so it was, and then many revisions took place over the years. And now what happens is that IceCube kind of sends out real-time alerts. Since April 2016, they have been releasing these real-time alerts of detection of high-energy neutrinos, especially greater than 100 TeV. And then one could start to search for neutrinos correlated with gamma ray sources. Primarily, these are blazars, where these are objects, these are extragalactic sources, active galactic nuclei, where the radiation is pointed towards the Earth. There have been sporadic claims initially, but there was no clear detection till 2017. Here you see a kind of list of what they would send out as alerts. They would give you the energy information. They would give you the time when this alert was sent out or when the event was detected. They would tell you from which direction in the sky it came, the right ascension and the declination. They would also tell you what is the angular resolution of that event. And then they would also give you a classification of what sort of topology this event is, whether it's a shower-like event, whether it's a track-like event, these kind of topologies you would send out. And I'll tell you why this topology is also very important. Now, this alert system has been upgraded in 2019. So IceCube kind of did away with their old system, which we were working many years ago. And now they have a system in place where they classify a probability of each alert to be of what sort of an astrophysical origin. So if it is of 30% astrophysical probability, it's called a bronze alert. If it's a 50% astrophysical probability, it's called a gold alert, which is like a purity of the signal that you want to say, that how pure this astrophysical signal is. And this is publicly distributed via what is called the Astrophysical Multi-Messenger Observatory Network, which is AMON, or a global network, so that the follow-up observations by other electromagnetic telescopes can take place. And again, the aim is to identify a possible electromagnetic counterpart. Then there is a second stream of alerts which IceCube also gives out, which is private alerts. These are not publicly distributed to the whole world. So they have certain MOUs in place with the electromagnetic telescopes. And for example, like MAGIC and Veritas since 2012, in the southern sky, the Hess Observatory in 2019. So they have a list. So these observatories prepare a list of sources based on their flux variability, based on their spectral shapes, and those which could become plausible neutrino emitters. And those source lists is followed by IceCube. And then if some neutrinos, excess neutrinos come from some of these sources, then they send out these alerts as a private information. However, from October 2024, IceCube has decided to discontinue the private alerts and make them all public. And so we are now currently discussing a preparation of a new source list for these alerts to come out. Okay, so now the important question is that which are these types of events important for as target of opportunity events for electromagnetic telescopes? So the field of view of these electromagnetic telescopes, gamma ray telescopes especially, are small and narrow. So they are typically of the order of between 3 degrees to 5 degrees. So they are pointed instruments. So you need to have good angular resolution for these telescopes, so for the triggers to come in. So hence, those ones which are really cascade events from IceCube cannot be followed up by the electromagnetic telescopes efficiently, because the cascade events have an angular resolution of almost about 10 to 15 degrees, sometimes a little better, but the average one is about 10 degrees. So within 10 degrees, your field of view is 5 degrees. You can only make a scan, but you cannot do much better than that. So the best events that you have to select are those track events where the typical angular resolution is of the order of a degree or even better than that. So only muon track events are generally used to follow up observations in the small field of view. So now let me come to the actual the scientific observations that on September 22nd in 2017, so through this AMON or GCN, IceCube sent out an alert that they had seen a high energetic neutrino, muon neutrino. And then and they alerted all the observatories and wanted them to follow this up because this was a very clean event and possibly of high astrophysical origin. And then on September 27th, Fermilab collaboration, which was following this up, found out that there is a blazar in the error circle of IceCube, very close to the best fit location of IceCube, which also showed brightening in the GeV gamma ray band. And this was the telegram which I was hinting at the very first slide. They sent out an ATEL, the telegram sent out by Fermilab, and then many other observatories started observing. MAGIC started observing already after getting the IceCube alert around 24th of September, and slowly MAGIC also saw a flare in VHE gamma rays. And then there were several other observatories alerted. So in the next days, you can see here a flurry of astronomers' telegrams kept on coming, most of them having seen flux variability in various other wavelengths from this source. Okay. So this is the kind of the MAGIC light curve, and other observatories like Veritas and MAGIC. Veritas initially did not see any emission, but later on they started to see emission also, primarily because this is a faraway redshift source, which makes it better for MAGIC, which is a larger telescope, to collect more photons in lower energies, and Veritas, being a smaller detector, does not collect that many number of photons. So they were statistically not seeing significant signal till they could integrate data over a certain period of time. So this is the kind of the light curve. So it's the flux as a function of time. And now I'm going to show you what the source was doing around the IceCube or before the IceCube alert. So this is the IceCube alert came. This is the kind of the flux variation a source, a kind of this type of source. So show when over a longer period of time, and you can see that during the IceCube alert there was, or even slightly before the IceCube alert came, the flux had already started to rise up. This was after the alert. In MAGIC, for example, when you see that initially we did not see much of a signal, but then again we started to see the flux rising, and then slowly it decayed, and then we carried on making more observations, and then we also saw variability in gamma rays much later period when there was also no IceCube neutrinos. The neutrinos were not detected then that time. So the first thing is to understand whether there is a spatial correlation between these things or not. So a joint analysis was done using a likelihood ratio test, and you calculate a chance probability estimated through this, which you estimate through this likelihood ratio test, and you disfavor the fact that this is just due to a fluctuation, that these are correlated just by fluctuation. You discover at about a 3 sigma level. The energy of the neutrino was computed to be pretty high, about almost 300. Maximum energy, or the most probable energy is about 300 TeV, with a lower limit of about 180 TeV and an upper limit of about 4.5 TeV. This all depends upon what sort of spectrum that you would assume in your Monte Carlo to derive the energy spectrum. And this is again the long-term light curve of the various observatories which we will go and find out. So this is the trigger. This is what it was doing in there were very few observations done on this source before IceCube really gave out the trigger, simply because this was not a source which was expected to emit very high energy gamma rays because it is at a quite a large redshift. When you have a source at very large redshift and if it is throwing out high energy gamma rays, you don't observe it simply because there is a gamma ray horizon. They interact with the extragalactic background light, the light which comes from all the stars and galaxies integrated over in your line of sight, and then the gamma-gamma pair production would take place. So you define what is called an optical depth, and that so you have the observed flux, which is the intrinsic flux multiplied by an exponential function, which is an optical depth dependent upon the redshift of the source and the energy of the photons that are coming from the source. So initially, we did not do many observations at very high energies because this was not really expected to emit very high energy gamma rays. But in Fermilab, which is a lower energy detector, GeV detector, you expect. So there are lots of data on Fermilab, and then you can see right before or around the ice cube trigger, there is a flare. In MAGIC, one showed, or in other high energy gamma ray telescopes, there was a flare after the ice cube. And then there are other wavelengths like X-rays and optical, where you try to understand the long-term behavior of the source before you start to go and do any sort of modeling with this. So before or after the flare, there was not much change in the spectral shapes seen. So there was no clear spectral variability. So a simple power law would also fit very well the data with an exponential cutoff. That is what I was hinting before, that if you have a certain source at a high redshift, then depending upon where your source is, what redshift, the photons of that energy will get attenuated, and you start to see curvatures in your spectrum. So higher the redshift, earlier the source starts to cut off. The lower the redshift, the source starts to cut off at a lower redshift. So this source was at a redshift about 0.34. So 0.34, you can, here I don't have the redshift, but 0.34. So this is at redshift of 0.5. You already see it's starting to show cutoff below 100 GeV. So that's why it was high energy gamma ray telescopes were not expected to see this source quickly. There were observations also carried out in X-rays or radio, optical, in various other wavelengths. So this kind of shows the long-term behavior again. So there was enhancement of flux in radio also seen quite a bit after almost 2 weeks after the alert was sent. But then radio comes from much bigger regions because these sources are powered by supermassive black holes, and they have jets in the system. And then the radio is far down the jet. So you do not expect radio emission immediately coming very close to the black hole, or close from where you do expect emission to come from either neutrinos or high energy photons. So that's quite consistent that you would see excess quite. The neutrino is just one. The neutrino is just one muon neutrino of 300 TeV energy. But the electromagnetic, yes, the electromagnetic emission has been going on for quite some time. And I'll show you what the implications of that means. So now, remember the earlier plot where I was talking about the spectral energy distribution, that if you put all these data together, you would then start to do modeling and then expect that you would be able to distinguish between the different acceleration mechanisms. This is the same plot I come back here, where you now see that all these kind of data have been put together, and now then people, so there were an explosion of theoretical papers in the archive once you start to put in all the data in the next days. So people started using various types of hadronic models, including leptohadronic models, pure hadronic models, photohadronic models. All these kind of models start to come in to the picture to try to explain the whole spectrum. In fact, one of these guys like Shan Gao and their collaborators, they even showed that even a pure leptonic model would fit the data quite well. So you do not really, even if IceCube had not detected neutrinos, you would be able to see, explain the whole multi-wavelength photon behavior of that. So they said that there was no need for any neutrinos in order to model the source. However, they could say that since IceCube has detected neutrinos in spatial correlation, however, we do not know whether the temporal correlation is really correct or not. But using models or the suitable model parameters, you could explain the leptohadronic model and put an idea about how much of the hadronic contribution would be there in order to explain the ice cube data. And for that, I told you before that X-rays also would play an important role, especially because when we worked on it, what we showed is that these events would also cascade to lower energies, to hard X-rays or soft X-rays. And so certain bounds can be got from the X-ray data, from the hard X-ray data, so that you do not overproduce the amount of flux in either high energy gamma rays or in the neutrinos. Yeah. So certain constraints can come from the hard X-rays also. So therein lies the importance of not just having gamma ray observations, but also X-ray observations. Okay, something very interesting which came from IceCube was right after that is that then they went back into their archival data to look for excess neutrinos from exactly from the source TXS 0506, and they found out that independent of the 2017 flare, the high energy event and the flaring event in gamma rays, there was already an excess of events they found out in their archival data. And but however, the more interesting thing came out is that when they looked at Fermilab data, it did not coincide with any flaring activity in Fermilab. So this was the IceCube events when it was not doing anything in or it was quite quiet during Fermilab. That threw you even more enigma to the whole thing, because then it raised the questions whether you really saw them in time correlation or not. So spatial correlation is well established, but time correlation you cannot really establish through that, because they saw once during gamma bright state and once during the gamma dim state. So it threw you up the question that whether they are really time correlated or not. Okay, so moving on to some more neutrino blazar coincidence story. So then after this, there were a lot of other tentative correlation studies done with IceCube neutrinos, with blazars in their field of view. However, in the last 2, 3, 4 years, however, there had not been any significant detection in any other wavelengths with that. So the only one which we found which was quite interesting was another source, PKS 0735, which is even at a slightly higher redshift. And it raised the question whether it is associated with an IceCube event or not, because the source was not very close by. It was about 2 degrees away from the IceCube best fit location. However, we did study this source in quite some detail using multi-wavelength data. And there, both Veritas collaboration and us, we together almost got out a paper, competing paper, but the conclusions were almost the same, that saying that you could actually constrain using hard X-rays from the constraints from the cascade emission. You need to use the hard X-rays. Veritas did not detect any high energy gamma rays from this source, unlike the one which was seen in TXS05. And of course, the question again, since it is even a larger redshift, there could be strong cutoff introduced due to the extragalactic background light, and hence gamma ray observations are not the most suitable ones in these kind of cases. Then there are some more. Now I move on to something slightly different, and as are coincident subthreshold events between Hawk and IceCube. Hawk is a water Cherenkov detector, which has a wide angle field of view. So it kind of scans the sky passes over it. It's a static detector, not like exactly like a telescope. And so these are subthreshold events, are those where the single observatory would not have been able to detect the hotspots or detect excess events coming from using a single data from a single observatory. But if you do a joint analysis of these events, you could say something interesting or not. So that's why these are called subthreshold events. And then there is a joint program between Hawk and IceCube, where they select temporarily the ice cube events within the transit time of the sources in the hotspot. And then they do a statistic to rank the coincident events. And then the overlap of the spatial uncertainties are estimated through a maximum likelihood method. What they found out in their three or 4 years of data is that there were only 2 coincident events such found. However, this is quite agreeing with the background. So you need to compute what is your false alarm rate, and that comes to about 1.5 per year. So within 2 or 3 years, 2 coincident events is perfectly compatible with what you get from random fluctuations of the background. In fact, if I spend 30 more seconds on it, that I would also have to edit this slide almost online, because yesterday night there was such a coincident event sent out. And so we were discussing pretty late in the night whether to follow up with gamma ray observatories or not, simply because the exciting thing this time in this event was there is a Fermi-Lat source sitting 0.1 degree away from the best fit location of both ice cube and Hawk. So that makes the life more interesting. So we'll see in the next days if we follow up with electromagnetic telescopes if something interesting comes out of it or not. So then there were also searches of neutrinos using hard X-ray sources, these active galactic nuclei. So these are motivated by environments where neutrinos can escape, but high energy gamma rays would interact either with matter or with low energy photons to cascade to lower energies. And so one looked at the X-ray catalog, which is a burst swift bat catalog, and then one performs a stacked search or an individual source search. And in that only there were 2 significant sources which were found out that could become significant in neutrino emission, NGC 1068 and NGC 4151. I'll come to NGC 1068 later, just in a minute or two. And there was no significant emissions shown from the non-blazar type AGNs. And and then there is another very interesting work which was done in the last 2 or 3 years, is to understand how much of the contribution of the ice cube neutrinos are coming from really from blazars. So one looked at these guys, Guillaume et al. Looked at Fermi catalogs and various other catalogs, sources in the ice cube error region of 90% ice cube error region, selected very good track-like events, and they studied that. And then they constructed multi-wavelength spectral energy distributions. And they found out that about 20 gamma ray blazars in ice cube 90% error region could be potential candidates of ice cube neutrinos. This is at a post-trial significance of about 3 sigma or so. So they claim that there is a growing consensus that the blazars will be counterparts of at least a certain fraction of the ice cube neutrinos. Now, as I come to the NGC 1068, so over a 9-year period of integrated search, IceCube gave their sky map, and of which there are 3 sources which showed up above the background. The most significant of that was NGC 1068, which was at a global significance of just about 4 sigma or so. Then next came is another blazar, which is a PKS 1424, and TXS, which was the famous one which made all this story, was actually 3rd in its rank in that 9-year full rank. So this PKS 1424 is also quite an interesting object because it has been earlier detected in gamma rays by the Veritas collaboration. And NGC 1068 is a completely different class of object. It's a Seyfert galaxy. So the difference between these they are somewhat less luminous in nature than the quasars or the blazars, where the whole emission kind of outshine the whole host galaxy. So you cannot really identify the host galaxy. However, in these kind of objects, which are called Seyfert galaxies, you can identify the host galaxies. They're somewhat less luminous in high energy radiation. Fermi-Lat had detected gamma rays from this source. However, there has been no very high energy gamma ray emission detected from there. So when you again put up all these together, the multi-wavelength IceCube collaboration put all these multi-wavelength data together, and they concluded that the neutrino luminosity was about 1.5 times higher than that of the gamma ray luminosity using Fermi as the pivot. Then some, how much? About 10 10 minutes? Okay. Okay, fine. Yeah, okay, fine. So, so I don't need to really rush everything through. So some more later news in gamma rays and neutrinos. So now moving on from the extragalactic sky and coming to our own galaxy, the Milky Way galaxy. So this is how the Milky Way galaxy, our galaxy, looks like in various wavelengths, like in optical, in high energy gamma rays, in if there would be the pion decay, the gamma ray emission coming through neutral pion decay. And then this was what it was expected if there would be neutrinos also. And this is what the IceCube put out in 2023, where they found neutrinos from the Milky Way. However, they were using cascade events which have a larger angular resolution, so they cannot really point to what type of sources these are. At the same time, there is in China, there is a large air shower, high altitude air shower detector, which consists of hybrid detecting mechanisms like scintillators, water Cherenkov detectors, and even imaging atmospheric Cherenkov detectors. So it's one of the largest air shower arrays now in the world. And that LASSO had detected a large number of sources, about 12 of them, which they claim have emission, gamma ray emission beyond 100 TeV. So all these are becoming potential, what we called pevatrons, that they can accelerate particles to PeV energies and beyond. And they become also potential candidates for neutrinos, neutrino emission. So then there was a study done a year back or so that about looking for neutrinos from the LASSO sources. However, they did not find any significant amount of neutrinos coming from at least the sources which were greater than 100 TeV or so. Okay, so I come to almost the end of my talk. It's what lies for us in the future. So in future, there would be the multi-kilometer cube neutrino telescope in the Mediterranean, which is the first rings have been already deployed in 2017, and steadily the array is growing. Then there was the proposal for IceCube Gen 2, making it IceCube much bigger. So you can understand that with IceCube right now, we are kind of scratching the surface. There is still a lot of things which we need to do simply because the rate of events is very, very low. So you need to increase the detector volume. So then there was this proposal for IceCube Gen 2, which would be the extended version of IceCube. However, this we recently learned that this is recently kind of currently stalled because no new construction. What NSF has put out or DOE has put up that there should not be any new construction. But we hope that somehow this impasse will be solved at some point of time. But at this moment, this is currently stalled. In the high energy gamma ray regime, that we need to improve the sensitivities to see some of the sources at higher redshift also and with better sensitivity. So a proposal which has already been accepted and is now going to be slowly going into the construction phase is called the Cherenkov telescope array, which will be an array of Cherenkov telescopes in two hemispheres, both in the northern hemisphere and in the southern hemisphere. One should look at the galactic plane, because which is better observed from the southern hemisphere, and the other would look more into the extragalactic plane from the northern hemisphere. The site is La Palma in the northern hemisphere in the Canary Islands, and in the south it's Chile at Paranal. And a partial array of CTA telescopes are going to be ready. The prototype 1 telescope is already ready and is operational at La Palma. And a partial array is hoped to be ready by 2026, because just a few days ago, the critical design review of these large size telescopes. So there would be different types of telescopes built to cover different energy ranges, because you cannot cover the energy range from using just one single telescope. So at the lower energy threshold, these are called large, these would have large mirror area. So they are large telescopes. At the medium energies between 100 GeV and few TeV or so, the traditional ones which we have been using over the years. And then at very high energies, you need to have a large collection area to collect even photons. So you will have small telescopes spread over a large area, like kilometer area, a few kilometers area. So this partial array is now getting ready. And so this is the improvement in sensitivity. There would be at least one order of magnitude improvement in the sensitivity to the current generation of telescopes. So we hope to see many more sources, and if IceCube Gen 2 also happens, so we would see many more triggers coming from these in order to do multi-messenger astrophysics. In the Indian context also, we have a telescope in Hanle now built by BRC, the MACE telescope, which is also slowly gearing up in order to make observations of these multi-messenger events. And then we have been also involved with making proposals in X-ray telescopes like AstroSat. With the optical telescope, especially, I have been running almost for the last 3 years dedicated optical observation proposal with Himalayan Chandra telescope at Hanle, and also the telescope at Aries in Nainital. And we also submit proposals for target of opportunity programs to AstroSat, all that. But all these, you understand that it requires a very, very tight cooperation between the different observatories, and it's not that easy to do this. So I slowly come to my conclusions that I hope I have been able to at least give you a glimpse of that blazars are plausible sources of very high energy cosmic rays beyond tens of PeV. Of course, they are definitely still not ultra high energy cosmic rays. These are cosmic rays of the order of 10 to the power of 15 to 10 to the power of 17 electron volts from what we see from the energy budget. So the detection of a blazar in flaring state in gamma rays in connection with a high energy neutrino event actually raises many more questions than it has answered. Okay. Main question that came up is, are they really happening during flares or not, when they go up and down or not? What about the temporal? We understand the spatial correlation now well enough, but we do not understand anything about the temporal correlation. So we need to build up statistics in order to understand that. But we currently have a few multi-messenger spectral energy distributions to play it, but it's still very, very model dependent. And as I said, that we need many more such events. We have been performing regular electromagnetic observations, and it's much more important to have tighter cooperation between these observatories to function together. But I say that I believe the future is quite, for the young scientists here, for the young postdocs, PhD students, the future is quite bright in this field with many more observations to come along. Thank you very much.
Thank you for that very comprehensive talk. And now we have time for questions.
Sorry, I couldn't catch if you said that the neutrinos that are detected in IceCube, are they the primary neutrinos from the astrophysical source, or
these are associated as of astrophysical origin? So they ride above the background of the atmospheric neutrinos. That's why you go to very high. You have to go to very, very high energies where the flux has actually gone down with a spectral shape of, let's say, 3.7 or so.
So I guess what I'm wondering is it possible that after a scattering, there is a very high energy neutrino that still comes out and then detected at IceCube?
The scattering of
some primary cosmic ray with some intervening.
So these are neutrinos. So they would be produced as protons, let's say, get accelerated in the cosmic ray, in the sources. If there is matter around, then they would have PP collisions, and then you would. So that's how the correlation study started.
How about in the intervening intergalactic gas or something scattering on them?
But these high energy neutrinos, I don't think they would be having that much scattering in this. That would not happen. But that's why the main motivation to look for correlations in gamma rays and neutrinos came up, because of using gamma rays, you could not go and say much more than a certain amount about what sort of acceleration is taking place, whether they're electrons or protons. However, neutrinos start to become the smoking guns, because then if you see correlations between them, you know that these are due to, the gamma rays are due to neutral pions and the neutrinos are from the charged ones. That's it. But these high energy neutrinos, the scattering is much less.
Neutrinos typically are detected? Is it a single?
They're always looking. They have a huge amount of atmospheric neutrinos. That's the major.
Very high energy.
The very high energy ones. How many events? There are quite few actually. So, for example, in this one, let's say when I talked about, for example, like these ones. like when they were doing this study over a period of, let's say, 3, 4, 5 years period study over, they had about 100 track-like events detected, which are of very, very high energies, beyond, let's say, 50 TeV or 100 TeV energy. Yeah, no, you could have different types. You could have multiplets, which are coincident in certain time window, and you count how much of them are. Pardon? So they define it as a kind of a threshold which is of 3 sigma, so that the amount of neutrinos causes a threshold, which is, let's say, 3 sigma, and then they immediately sent out an alert. That's the multiplet. And then many of these track-like events are single ones, just one single neon ones. So these ones are, the others are the ones which I was talking about here in the private alert system. Let me go back there. These are multiplets. So these are kind of multiplets, flares. So these are what you call neutrino flares you see already in the online system, which cross a certain threshold of 3 sigma. And then immediately they send out the alert. But they don't, what they do is that basically, because to take care of the trials, they mute the system as soon as they send out the alert, because they don't keep growing. That's why the how many number is difficult to ascertain. Then the threshold has to fall below the 3 sigma again to the system to become active to send out again alert. They do this because otherwise they would have troubles of taking into account all the kinds of trial factors. Because you have trial factors that self-triggering trial factor also, no? How much of it is self-triggered? Because if you are building up on the same statistics, you have you are also triggering doing the self-trigger. So that trial factor correction is very difficult to take, as I understand from discussing with them. And that's why they mute the system as soon as they send the alert. And then it falls below 3 sigma, and then again, after it crosses 3 sigma, they will send out another alert from the same source. So they have a source list. They keep monitoring the source list, and they do real-time analysis of that. And these are the multiplets. The other ones, which are mostly given out as public, are track-like events.
This galactic plane, I'm
Yeah.
a little confused. It looks to be kind of perpendicular to
No,
the
so
equator. I
so
mean, how is the-
ice cube is mainly seeing neutrinos from the northern hemisphere.
Correct, yeah.
Because it's in the south.
Yeah,
They have
okay.
some sensitivity
Okay.
to the southern hemisphere, part of the southern hemisphere.
Mhm.
And then this is the galactic plane.
Sorry.
This is where the galactic plane is
Oh,
around. So this is the way the galactic plane you see is this kind of region.
I'm seeing a dashed line which is kind of vertical. Maybe I'm mistaken.
This one? No. This
A
one.
dashed line.
So this is what ice cube would see as the galactic plane when they see it from the southern hemisphere, this part. This is the one. Because you are in the south, you are
Yeah.
looking in the south, you are looking in the north,
Okay.
and then this is the part which you see as the major part of the south. And then the part of the plane is also the Cygnus region, for example, is in the north, in the northern hemisphere.
Oh, it's not exactly below. Oh,
yeah.
because of the
So a
tilt.
part of
Okay,
the
no.
plane is also in the north, a very small part, which is the Cygnus region. And then the majority of the part is in the what you see.
So this blizzard that was associated with this event, so it was known from before or after this event you
The blazar was known. So there is a lot of data optically, for example, if I show you the long-term here, the long-term curve. So this is the optical data of the long-term optical data over several years actually, and radio data over several years. So the blazar was well known. So it's a Texas source. TXS is basically a catalog where the Texas radio source. And the only thing which we did not know about is that whether it would emit high energy gamma rays or not. As I was explaining, we did not expect it because it was at a higher redshift. So we did not have observations in high energy gamma rays. Whereas in low energy gamma rays, once Fermi became online around 2008 or so, they have been observing low energy gamma rays or medium energy gamma rays from this source. So the source was well established as a source in electromagnetic spectra. The only thing which we did not know is that whether it emits in high energy gamma rays or whether it's a plausible source of neutrinos or not. In fact, it was a little bit of a surprise because before this was discovered, most people believed that those sources would be the best candidates where you have a large number of photons around the source because P gamma interaction will take place and produce neutrinos, right? But this source is a much more cleaner source. And that created a lot of excitement that how come these sort of sources which were not really expected to emit neutrinos could emit. It turned out that this source is a kind of a masquerading source. So it has emission lines and a lot of photons, but the jet luminosity is quite high that they masquerade as a kind of a high frequency type of sources. So initially it was not expected, but there are surprises always when you.
So also I wanted to ask another thing is that what is the probability of identifying a new source with this type of event? Is there?
Okay, that's a good question, but a difficult question is basically because within the ice cube error box, let's say these track events, these are typically of the order of a degree, sometimes better than a degree or so. A new source is, there could be tens of new sources there, especially if you look in optical, because where you have arc second and arc minute resolutions. So you could have many optical sources there. Then in order to really classify which is your source, you have to do a very thorough likelihood analysis to understand whether they are or not. And but you would expect that those sources to also emit high energy gamma rays or X-rays. They may be quiet in gamma rays simply because the environment may be killing the gamma rays down, but then they would at least see it in X-rays or so. So that's where the motivation of preparing the source list comes. You take into account all this available multi-wavelength information in order to prepare a list which would be the most plausible sources. IceCube also looks for all sky events and looks for unknown sources also. But these are more sure because there you are swamped by your trial factors. Because the whole sky you have to account for your trials. Here, since you have a source list, your trial factors are less, and hence your significance will be boosted.
So you mentioned about this leptohadronic and photohadronic models to model your photon spectrum. Can you say about what is the process that it is trying to model?
So basically, these are P gamma and PP interactions, and then
what is leptohadronic?
So you try to so there are also electrons in your system. And so it's not a pure hadronic model. When you call it a leptohadronic, it means there are electrons and protons in your system. You then try to understand what is the contribution of electrons and what is the contribution of hadrons to the emission, high energy emission that comes. So the leptonic emission would be through synchrotron and inverse Compton. Whether that is the dominant emission, then you of course do not need any neutrinos to fit your data. If you would need neutrinos to be there along with this photon emission, then you would need to have a dominant proton contribution along with your electrons. They are there, of course, because in cosmic rays, of course, the main question is that 98% of them are protons, only 1% of electrons. But most of the cases we see gamma ray emission, but we did not see neutrino emission. There are two cases. One, we have an observational bias. We are always looking for such sources where you see electrons mainly. And then, of course, neutrinos are hard to detect. So once we start to detect many of them, then we can play this game better.
Thanks.
Any other question? So maybe I will ask you a very naive maybe. That, you mentioned about temporal correlation, but what I would expect is that the neutrino will come like earlier than the photon, right?
Right.
So spatial correlation is understandable.
Temporal correlation is very difficult. It's very difficult. So these Shangao people actually did correlation studies of like if the neutrino would be emitted 90 days within a time period of 90 days, 180 days, and then they tried to model this. So in this one, I don't remember whether I had put that information, but I can give you the paper where they had put this information about that what would be the temporal correlation required to see between them. However, they could not really establish a very tight temporal correlation. It's very difficult.
Okay, thank you for that very, exhaustive talk. So next speaker is Abhi.
So let's go back a bit more in cosmic timeline now. So I'll discuss about the traces of early matter domination and through its impact on the decoupling of dark matter and formation of small scale structures. So this talk is based on this recent work in collaboration with Deptosh from IIT Kanpur and his students Orpon and Sariful. So I will give first a brief overview of where I'll basically tell you the main point of this work, and then I'll go into the details of the discussion. So essentially, the existence of an early matter dominated epoch prior to the Big Bang nucleosynthesis impacts the thermal decoupling of dark matter. If the dark matter decouples during the matter dominated epoch, then it undergoes an additional amount of cooling compared to the plasma temperature. And this additional cooling, the rate of the cooling, it depends on how entropy injection is going into the plasma during the reheating epoch. So this rate depends on the entropy injection. And this in turn actually reduces the free-streaming horizon of the dark matter. At the same time, there is another aspect of an early matter dominated epoch, which is the matter perturbations grow linearly during the matter domination. Now, if you combine these two effects, the linear growth of matter perturbations and reduced amount of free-streaming horizon of the dark matter, this together tells you that there would be a boost in the sub-Earth mass halo population. And as a result, what may happen is amplification of the dark matter annihilation rates in the galactic centers, which are in principle should be able to give some probe to the early matter dominated epochs through, let's say, the Fermi-Lat observations. So that's the main point. It's extremely simple. Now I'm going to discuss the details, starting from the motivation for considering an early matter-dominated epoch. So this cosmic timeline have been shown several times in past 2 days, and most of the concentration was towards this region, which is more near to us. There are constraints, observations on from cosmic CMB and let's say JWST and others. But these observations, they essentially constraints, or they essentially probes the much later time in the cosmology. But virtually there are no observations between the inflation and the Big Bang nucleosynthesis. So we almost know nothing about how the universe was in between these two periods. However, the most important thing is that interesting particle physics events, almost all of the interesting particle physics events, electroweak phase transition, QCD phase transition, maybe dark matter generation, baryogenesis, everything happened here. So it's extremely important to understand and probe this epoch of cosmology. So the lack of any observations leads to speculation. And one of the most popular speculation about how the universe was before the Big Bang nucleosynthesis is a matter-dominated universe, which is different from the usual lambda CDM cosmology, where after the inflation, an instantaneous reheating happened and the universe was entirely radiation domination. It's a deviation from that. It's an alternate scenario with a matter domination. And this is quite natural in a sense, because if after the inflation, the inflaton has to sort of decay in a way to the thermal plasma and gives rise to reheating. But typically this process of injecting entropy into the plasma, it's not an instantaneous one. It takes time. And this epoch of reheating, it is essentially a matter-dominated epoch if the inflaton is a matter-like object. But there are many other motivated scenarios. Various BSM scenarios predict metastable fields which can dominate the energy of the universe in the early universe. Examples are moduli, dilaton, curvaton. There are multiple. So there are plethora of scenarios where it can go on. And this leads to, after the inflation, this leads to a universe where some oscillating scalar field is dominating the energy of the universe. And at some point, it decays into the thermal plasma. It injects all its entropy, transfers all the entropy to the standard model bath, and its energy density sort of exponentially falls off, and the universe gets reheated into the plasma. The only thing that has to happen is universe has to be radiation dominated prior to the Big Bang nucleosynthesis to evade the constraints from BBN. And that's around a few MeV of temperature. So it has to happen before the few MeV temperature. Now, what's not so well established or well studied is how this entropy injection is happening. So most of the scenarios that people discuss is sort of a scalar field perturbatively decays through a zero temperature decay. And so the dissipation is just a constant. Dissipation rate is just constant. But it often happens that this is not true. In fact, in general, the rate of entropy injection depends on the plasma temperature as well as the expansion of the universe. So it depends on the field value of the scalar that dominates the universe. So there are different specific scenarios, specific models, and specific analysis using the thermal field theory, where you can actually compute how this entropy injection is happening. There are multiple papers. I have just put some of them. Some of the detailed papers are by Mukaida et al. But for our purpose, what I can do is we can just parameterize the entropy injection as a sort of a polynomial of with some t to the m and phi to the k, where m and k are some, let's say, some integer exponents. And if you take such a dissipation rate, then the temperature, the evolution of the temperature of the thermal bath, that actually depends on these exponents. It's a model dependent point. And I'll show how this, I'll show some examples of that. So the question is, what are the fingerprints of such early matter dominated epochs? Can we distinguish between these different scenarios? Can we actually pinpoint how the rate of this entropy injection was? So that question is the question that I want to answer. And for that, we use the dark matter sort of as a probe. So let us look at how dark matter decouples during an early matter dominated epoch or in any non-standard scenarios. So thermal decoupling is essentially chemical and kinetic decoupling. And the chemical decoupling goes through number changing processes of the dark matter. So it's through the annihilation, for example, for thermal dark matter. And this process also sets the Rayleigh density. So chemical decoupling sets the Rayleigh density. And in a early matter dominated epoch, what happens is you are injecting entropy to the system. So the Rayleigh density becomes diluted. So what the Rayleigh that you expect in a normal lambda CDM cosmology, if there is some early matter dominated era, then the Rayleigh could be smaller than that. So as a result, for a thermal dark matter, for a freeze out scenario, you would expect you need smaller cross section, smaller annihilation cross section, and therefore smaller couplings of the dark matter with the particles in the thermal bath. If you consider a freezing kind of scenario, then the situation is opposite. Then you require larger cross section to produce the dark matter, and so larger couplings. In fact, this can be used to see if so freezing models, they require really small couplings, right? But in the presence of such an early matter dominated epoch, you require larger coupling, and so some of the freezing scenarios which you you have no hope of probing might come under the experimental radar if such an epoch is present. So this is all about chemical decoupling. Now let's go to the kinetic decoupling. Kinetic decoupling is decided by the elastic scattering of the dark matter with the particles in a thermal bath. And after the decoupling in a radiation-dominated universe, dark matter, the temperature of the dark matter redshifts as a to the minus 2, while the plasma redshifts as a to the minus 1. So the dark matter actually cools faster than the plasma. And this sets the free streaming horizon of the dark matter, which also in turn sets the smallest scales at which you see some structures, because above this, below this free streaming length, then all structures are washed out because of the velocity of the dark matter. So the chemical decoupling, the kinetic decoupling sets the free streaming horizon. Now, in usual scenario, typically chemical decoupling precedes kinetic decoupling unless you go to some very light dark matter or something. So what happens in an early matter dominated epoch? So in early matter dominated epoch, so you have to actually solve the equation for the dark matter's temperature, the evolution of the temperature, and the solution actually, and this equation depends on the momentum transfer in the elastic scattering. So this momentum transfer can be like, you can have an elastic scattering with an S wave scattering or a P wave scattering or even higher wave scatterings. And the evolution of the temperature depends on it. So the solution actually involves two terms. The first one term is just goes as a to the minus 2, which is the usual. And then there is another term which goes as some a to the minus p, some other powers, and it depends on how the expansion history and the elastic scattering rate. So just for example, I've just given one example here. So let's say that this entropy injection rate, the dissipation rate just depends on temperature. In that case, the plasma temperature before reheating falls off as a to the minus half. And these are the these two lines are the evolution of the dark matter temperature for S wave and P wave scattering. And you see in one case it falls off as a to the minus 1, and in the other case it goes as a to the minus 2. And after the end of the reheating, then in both cases it goes to a to the minus 2. So in this case where it goes as a to the minus 1, we call it a partially decoupled dark matter. It's a partial decoupling. It's not as fast as a to the minus 2, and this is a full decoupling. So it depends. So that how the dark matter decouples, it depends on how the universe expands and how the dark matter scatters, how the dark matter elastically scatters. So again, giving you two more examples. So where entropy injection rate is constant, in that case, S wave scattering cannot decouple the dark matter. P wave scattering can only partially decouple the dark matter during the early matter dominated epoch. While if the entropy injection rate depends on the temperature of the bath, then S wave scattering can partially decouple the dark matter and P wave scattering can fully decouple the dark matter. All this leads to a reduction of the free streaming horizon of the dark matter. So these are the three situations we are showing with different expansion history and with S wave and P wave scatterings. And this colored region in these three plots shows that where the free streaming horizon of the dark matter is smaller than what you would expect in a fully radiation dominated cosmology. But there is a catch here. The catch is that this sort of holds true only if there is a single process which operates both the chemical decoupling and the kinetic decoupling. If there are multiple processes present, some of which are dominantly contributing to the chemical decoupling and the others contributing to the kinetic decoupling, then it's not so easy to say that the free streaming horizon would always decrease if there is an early matter dominated epoch. So that's the story about the decoupling and the free streaming horizon. Now let's come to the what happens to the matter perturbations. So the matter perturbations actually grow linearly. The dark matter perturbations grow linearly during the matter dominated epoch. So let's take this line. So around this point, the mode that we are interested in enters into the horizon, and then it grows linearly till the universe was matter dominated, and then then it becomes radiation dominated. And this linear growth in the matter perturbations, this can also be seen in terms of the power spectrum, where you can see that this red line gives you a growth, a deviation from the usual matter perturbation in the radiation dominated universe. But there is an important point here. This growth is not, this growth cannot go on forever. It depends also on the free streaming horizon of the dark matter. And beyond the free streaming length, this actually sharply cuts off and just exponentially falls off. So this actually tells you that the matter power spectrum is enhanced during AMD in a range between the sort of reheating and the determined by the reheating temperature and the free streaming horizon of the dark matter. And this leads to enhancement of the halo population. So this object in the y-axis is called the differential bound fraction, which already I think Ranjan showed in the last yesterday. And you see the populations of the dark matter of the halos with mass below the Earth mass gets a boost within two scales. One is upper cutoff determined by the reheating temperature, and there is a lower cutoff, sorry, one should be lower cutoff, determined by the free streaming length or free streaming horizon of the dark matter. And the interesting point here is this green line. This green line shows that there is an upper value of a cutoff on the free streaming length, beyond which you would see absolutely no structures. So we thought that this can be turned into a constraint on the parameter space of dark matter models. And that is exactly what we have done. We have taken two different dark matter models, very simple toy models. One is a scalar dark matter and one is a fermionic dark matter. And in the first case, there is an S-wave scattering and partial decoupling, and the second case, P-wave scattering and full decoupling. And we show that actually we can find some region in the parameter space where the decoupling happens during the early matter dominated epoch. And there is some region, there is a line which separates this parameter space where you can actually see an enhancement in the small scale structures. So this is also shown in specifically in this differential bound fraction. And this is my last slide. So what we are now doing right now, what we are working on is to, so we already found the boost in the structure formation, boost in the halo populations. Now we want to see how this affects the dark matter annihilation rates in the galactic centers. This actually depends on two competing effects. One is the lower annihilation cross-section required to fix the relic density, and the other is the higher micro halo population. And one has to multiply both of them and see whether ultimately the boost persists or not. We are hopeful that this will be the case for certain kind of entropy injections, because, for example, if the entropy injection is proportional to temperature, then the annihilation cross-section you require is actually greater than what it would be for a constant entropy injection. So, so this is an ongoing work, and this would probably give some more handle to probe this kind of non-standard cosmologies and distinguish different dark matter models. So thank you very much. Thank you for inviting me, and thanks for your attention.
Questions?
So in all of these studies, you're already assuming that you have a standard model bath already formed. So dark matter is always weakly interacting.
Yes, here we are assuming that the dark matter is a WIMP dark matter. It's a thermal dark matter.
And then how is it ensured that always a bath will be formed? So it is the standard model particles are strongly interacting with your inflectron, or?
Yes, so the standard model particles are produced from some dissipation of the inflaton. That's the assumption. And also there is another assumption, since you pointed it out. The assumption is that the thermalization is instantaneous. So once the standard model particles are produced, they instantaneously thermalize. It's not always true. And those effects have also been studied by Deptosh and his students. And then there are also interesting things if you assume that the thermalization is non-instantaneous.
And what happens to these dark matter particles? So they're beyond standard model particles.
They're beyond.
In the inflaton phase, it was already strongly coupled with the inflaton. At some point, some decoupling happened. So how do you take into account that?
What we assume is that the dark matter is produced so dark matter is in thermal bath initially. It's a thermal dark matter, and then it frozen out below, let's say, roughly the mass of the dark matter. When it becomes non-relativistic, it freezes out. That's the chemical decoupling. But chemical decoupling does not mean thermal decoupling. So then you need to also see whether when it decouples kinetically. And that says the freeze terminal.
Thank you.
Yeah.
Another question? Yes, Ram.
Hi, thanks for the nice talk. So you said the kinetic decoupling using the elastic cross section, but so I don't know about whether that effect is relevant here or not, but there is also another effect due to dark matter radiation coupling, which can produce acoustic waves, acoustic oscillations, and that will suppress the power spectrum. Is that relevant here, or do you know? I don't know the answer.
I also don't know the answer, but this happens much before the BBN.
Yeah,
so
this also what I'm talking about is also will
okay,
happen
so
much
then
before
I
the BBN.
don't know the answer. Yeah.
But yeah, okay. Okay, thanks.
So one of the plots that you had, you showed the change in the power spectrum. I forgot if it came. Yeah, this one. So is the scenario that the changes happen without screwing up any constraints? Is that?
Yeah, because
So
these
it
are
happens at-
all happening before the BBN. So there is, I don't think there's any constraints on this kind of scenarios.
So meaning the change is at large K. And so there are observations that don't yet constrain this.
No, because you see this, the boost in the halo masses, these are very, very small. These are sub-Earth mass halos. So the large scale surveys won't capture any of
Small
this.
K behavior would be standard.
Yeah, so the only way I think to capture this is to see the dark matter annihilation rate, and there may be some boost in there.
Thank you.
So let us thank Bobby.
Thank you.
Which will be by Biplab.
Okay, so first I would like to thank the organizer for inviting me. So today I'll be talking about long-lived particles, some unconventional signatures. And this talk will not be very technical, so I have made some basic slides. Okay, so we all know that so far we have not found anything, and there are many possible reasons. And one of the reasons may be the following, that probably we are producing new particles, but the search methods are not very sensitive, so that we are not been able to see those particles. Okay, so or the signals are experimentally challenging. So one such possibility is long-lived particles. And yeah, so before I talk about long-lived particles, let me talk about some kind of recipe for conventional searches. Suppose you have a model, given a model, suppose you have a new particle X and you want to search that particle. So first you will check how to produce that particle in the collider. So whether this particle can be produced singly or whether you can produce it from the decay of some standard model or beyond standard model particles, or single production is possible. And the second one is like how this particle decays to other particles, like whether it decays to standard model particles or whether it creates a cascade. So this kind of questions we first ask. And at the LHC, we can identify electron, muon, photon, and quarks and gluons in terms of jets. Okay. And you can also identify the presence of invisible particles like neutrinos or dark matter in terms of missing transverse energy. These are actually my observables. Or so based on this thing, we actually classify signatures. Suppose you have a production mechanism and you know the decay mode, so you actually classify according to the production and decay modes. Like say for Higgs boson, we actually search for diphoton or four lepton because Higgs boson decays to those particles. And then we actually do some kind of analysis to separate signal and background. Okay, so now say take one example, like say suppose you have a particle called gluino that decays to QQ bar and a missing energy particle. This chi bar is actually dark matter. So you can pair produce this gluino. So and this gluino will produce some quarks QQ bar. So the final state will be multiple jets plus missing transverse energy. Okay. So and then you define some variables and try to find the signature of gluino. Okay. But now let's consider the possibility that for some reason, suppose this gluino is long-lived. Here long-lived means we are actually talking about LHC. So the decay length is say starting from a few millimeter to a few hundred meter. So we are talking about this kind of decay length. Okay. So I'm saying that this gluino is somehow long-lived means this decay width is suppressed for some reason. Okay. So in that case, gluino will be pair produced, but it will not decay instantaneously. It will probably travel through the detector, but gluino has some color charge, so it will hadronize and form some kind of heavy hadron called R hadron. But the point is that here, if the gluino is prompt, then the signature is multiple jets plus missing energy. But here, gluino is now semi-stable, but we don't know what would be the signature, but it's no longer multiple jets plus missing it. So the point is that if the signature is different for prompt gluino and long-lived gluino, but you can ask this question like, so probably we are actually like fine-tuning the situation and we make this gluino long-lived. Probably it's like probably not possible or it's too much fine-tuned. Okay, so let's see. In the standard model, like there are many long-lived particles and like presence of long-lived particles is not really unnatural. Think about neutron, say B plus, meson, pion. There are many long-lived particles in the standard model. And there are actually several reasons. Think about the pion decay. Pion is long-lived, charge pion is long-lived because you have a heavy W boson propagator in the decay. Neutron is long-lived because neutron decays to a proton and the mass difference between neutron and proton is very small, say 1.3 MeV. That's why this decay is phase space suppressed. This decay is actually suppressed because of the propagator, heavy propagator. And there is another example like this B plus decays to some two particles. You also have a W boson suppression, but additional suppression comes from small CKM element in the coupling. That's why B plus is also long-lived. So you have like three reasons, like one is coupling suppression, phase space suppression, and heavy propagator. That's why like standard model particles are long-lived. We can apply the same argument for beyond standard model particles. Say, suppose you have this particle that decays to E plus, E minus, and neutrino, but here this coupling is actually it comes from R parity violation. This coupling can be arbitrarily small. So in that case, this particle will be long-lived. I have already talked about gluino. Gluino is long-lived. Think about this decay mode, like gluino decays to QQ bar chi10 through a virtual quark. If this quark is very heavy, in that case, this gluino can also be long-lived. It's actually propagator suppression. Here it's coupling suppression, and here this charge or this charge particle is long-lived because the mass difference between the charge particle and the neutral partner is very small. So in case of say some specific model, it can be as small as a few hundred MeV. So in that case, this particle is long-lived. So I am using these three arguments: small mass difference, like phase space suppression, heavy propagator, and small coupling. So this can be applied to beyond standard model cases also. And probably we are aware of like many models called dark sector models, where you have standard model and you have a dark sector, and these two sectors are connected by some kind of mediators called portals. So if this mediator is, say, gauge boson, we call it dark photon. You can have dark scalar, you can have scalar portals or neutrino portals. And you can also think of some other higher dimensional operators like action-like particles and many other things. But the point is that here this portal couplings, this epsilon or kappa or y, can be very small. In that case, these mediator particles can be long-lived. Okay, so what I'm trying to say is that in many beyond standard model scenarios, you can naturally get long-lived particles. It's not really unnatural. Okay. Now, no, they are not dark matter. Yeah. Okay, so now, so let's talk about the simplest scenario. Say you have a particle X that decays to standard model particles, and you have a coupling lambda which is small. That's why this X is long-lived. Now, so we can actually make this coupling very small, and we can change the lifetime of this particle. So it's easy. But the problem is that this particle, suppose I want to produce this particle by using the same coupling, like standard model particle will collide and it will produce this particle X, then we are also using the same coupling in the production vertex. So in that case, the total cross section will also be suppressed by the same factor, lambda squared. So in that case, if you like in this model, if you make this particle X very long-lived, in that case, the production cross section will also become very small. Okay. So this is actually some kind of minimal model, but we can also have other models where this LLP can come from the decay of some standard model or beyond standard model particles, or the single production of LLP is suppressed, but not the pair production. So in that case, you pair produce the LLPs, and the decay will be determined by different couplings. Okay, so in that case, you can have reasonable cross section. Okay, now let me give you one example of LLP searches. Like here, again, I am talking about strongly interacting particle, but this gluino is not long-lived particle. So we pair produce gluino, but this gluino decays to some quarks which will form jets, but to another particle which is long-lived. Gluino is prompt, but this X is long-lived. But you see that from the decay of gluino, you have some prompt jets. So you can have multiple prompt jets, and you can search this scenario using multiple prompt jets and missing energy. This is possible. But the point is that we are not fully utilizing the features of this process because we are not really considering the presence of these long-lived particles. We are just focusing on prompt particles which are coming from the decay of gluino, but not the LLP. So in reality, this will happen, right? So in addition to those prompt jets, you will always have this charged long-lived particle, and that will travel, and in this situation that it will travel up to some finite point, and then it will decay to probably some dark matter and some soft particles. So this is actually something called disappearing charge track signal, because you will see this track up to some point and then you won't be able to detect those particles. So this particle will disappear. Okay, so this is a classic signature of long-lived particles. So probably you can say that, okay, so let's search this process using multiple jets plus two disappearing charge tracks, because we have this thing in the final state. So I just want to show one example that, see, let's not go into the detail, but see, this is actually this charged particle and this is the gluino mass. So just consider these two lines. One is this line, this blue line, which actually is the limit on this, on the parameter space, where we have not considered the presence of long-lived particles. And then the limit is stronger and this limit is weaker, where we have actually considered the, where we actually considered the presence of these disappearing tracks. So we considered, we have taken additional information, but still the limit is much weaker than the prompt search. The reason is the following, that in this analysis, the Atlas collaboration, they are actually, the question is how to identify that disappearing track, and they assume that the length of this disappearing track should be at least 50 centimeter, but the typical decay length of this particle is 5 centimeter. So you'll always have, we have only a small amount of events where this particle will propagate up to 50 centimeter. So we are actually losing events because of this kind of strong conditions. So in that paper, we actually considered other possibilities, that we should probably try to construct shorter tracks. And nowadays, actually, like both CMS and Atlas collaborations have done major improvements in their analysis, and they are now talking about tracklets, means shorter tracks, shorter disappearing tracks. Okay. And this is another example. So here you produce this long-lived particles phi that decays to BV bar. Okay. Now see, consider this line. This is actually some kind of exclusion limit. Consider this black line. So here you see, this is actually the limit for prompt search. So the point is that, you see, as we increase the decay length of this particle, the limits are actually become stronger, and then suddenly it becomes weaker. Okay, the reason is the following, that in the final state you have B quarks, or that will form BJs, and when we search for BJs, there we actually search for some kind of like some kind of secondary partices, some kind of long-lived particles in the final state. So because of this phi, which is slightly displaced, you will be able to identify those BJs more efficiently. That's why the limit becomes better. But after some time, if this phi is highly displaced, then you won't be able to identify those BJs, and then the limit will become weaker. Okay, so what I'm trying to say is that, so you can actually search long-lived particles using existing prompt search analysis, but that won't be efficient. So you need some kind of dedicated analysis in order to search these scenarios. Okay. Okay, so I'll just talk about a few unusual features of LLPs. One is, suppose let's consider this scenario. This, you have produced this X, and X decays to E plus E minus. Okay, and think about prompt scenario where you produce X and that decays to E plus E minus. So what would be the signature? What is the definition of an electron at say at some experiment, say CMS? So the definition of electron is the following, that you will have a track in the tracker, and you should have energy deposition in the electromagnetic calorimeter, and you should not have any energy deposition in the hadronic calorimeter. So if this particle X quickly decays inside the tracker, that's the first part of the detector, you will observe these two electrons and you will be able to identify this particle X without any problem. But now this is LLP, so there is a chance that this LLP will travel up to some point and it will decay to E plus E minus. There is a chance that if the LLP travels like a few centimeters, then this electron, this track reconstruction algorithm may not work, and in that case, you may not be able to identify those tracks coming from electron, but you will be able to see the energy deposition in the electromagnetic calorimeter. Okay, so but that's how we identify photon in the experiment. You should not have any tracks in the tracker, but you should have energy deposition in the electromagnetic calorimeter. So this LLP decays to E plus E minus, but it looks like a photon. Okay. The third option is that this LLP travels further and it decays inside the hadron calorimeter. Okay. So in that case, there is no track in the electromagnetic calorimeter. There is nothing, no energy deposition in the electromagnetic calorimeter, and you have energy deposition in the hadronic calorimeter. So this means that it will look like a neutral hadron. Again, it decays to E plus E minus, still it looks like a neutral hadron. And the last one is like this LLP travels, it passes through all the detector part and it decays outside. So in that case, it will look like some kind of invisible particles. Okay, so what I'm trying to say is that for prompt particle, we actually, if we know the decay products, that is sufficient to define the final state. Here, it not only depends on the decay products, but also the lifetime of the particle, where it decays. So depending on the position of the decay vertex or decay position, you will see different final state. That's why it's actually more challenging, and you need some kind of dedicated algorithm to identify those situations. That's why it's actually, you have added another dimension, which is the lifetime. Okay. Okay, so there is another strange feature of this is of LLP. The point is that it's the following. So suppose this is one calorimeter cell and this is the interaction point. So if one particle hits that calorimeter cell, and we know this angle with respect to the z-axis is 30 degree, then we'll say that this calorimeter cell represents theta equal to 30 degree. And this calorimeter cell is 20 degree because if some particle starts from this point and hits that particle, then the angle with respect to the z-axis will be 20 degree. So that's how we actually align the calorimeter in terms of pseudo rapidity. Okay, but for long-lived particle, consider this long-lived particle, it goes like this and then it decays to two particles, and this particle hits the same calorimeter cell. Okay, so how do you actually, what do you tell about this particle? You will say that, oh, this particle is coming from the primary vertex with angle 30 degree. But it actually, probably the angle is different because it comes from this point and it moves like this because it travels up to this point. So this will actually create some kind of non-trivial effect on the analysis, and this kind of effect you won't be able to see if you do some kind of fast simulation, because layered segmentation and all these things are not there in the fast simulation packages. So you won't be able to see that. Okay, so this is actually non-pointing thing. So one example is the following. Suppose you have a Z boson that decays to two quarks, and I place this one quark here, and then another quark will move in a circle, right? So this is the second quark. If we actually specify the energy of this particle, then the angle is fixed. Okay, so this is the first quark and this is the second quark. It's actually jet. So in that case, if you actually average over multiple jet images, it will look like this. But if this Z boson is displaced, then this nice structure will be lost, and you see that there are actually multiple effects, and you won't be able to see this nice kind of gap between two jets because of this misalignment. Okay, and there will be other effects like the physical area taken by the decay products would be smaller and smaller, and it will depend on the decay length. So this feature will be lost. And the machine learning can actually, some kind of image recognition can identify this kind of strange jet events. Okay, and there is another strange feature, which is this is actually non-pointing nature, but in some cases the decay products of the long-lived particles can also come back, it can move in the backward direction. If the long-lived particle is heavy, it can also, suppose this gluino is moving in that direction, but some of the decay products can also move back to the in the backward direction. Okay, So then, okay, so I just want to tell you that the question is, how do you actually identify the signatures of long-lived particles? Again, let's consider this example that phi, you produce this long-lived particle that decays to E plus E minus. So you start from this point, this LLP, it goes slowly and it reaches here and it decays to 2 particles. Okay, and then the decay product hits this calorimeter cell. And suppose you know how to measure the time. Okay, suppose you know where it starts T0 and you know T1, and this LLP moves slowly because it's heavy LLP. In that case, you can actually calculate the time difference T1 minus T0, and you check this time difference with respect to some prompt particle that starts from here and hits here. So this time delay would be more for long-lived particles. Okay, so in principle, you should be able to identify the time delay, and in like experiments, there are some parts like electromagnetic calorimeter, and in future MTD will be there, so which can measure the precise timing of these particles, and from there you can actually construct multiple variables, and you can separate long-lived, like the signature of long-lived particles from prompt particles. But I want to show you one. This is actually some kind of like timing variable. It's some kind of energy weighted timing variable for jet, and you see this is the distribution. So, but if you see that there's a actually red line which is coming from QCD jet, so-called prompt particles, standard model background, and this blue line is actually from some long-lived particle scenarios where the mass of this particle is 30 GeV, but the decay length is 10 centimeter. And this is another LLP scenario where the decay length is 100 centimeter. You see that if the decay length is 100 centimeter, you can separate signal and background easily. But if the decay length is 10 centimeter, it's not very different from QCD jet. But I already told you that probably in the standard model, all these particles are prompt, it should reach fast, right? But it's not true because of this QCD. QCD has a long tail, this distribution, and the QCD cross section is huge. And there are various effects actually, like the intrinsic spread of the beam spot in the temporal and longitudinal direction. You have some long-lived particles in the standard model also, like K short and many other particles that can also create some kind of time difference and the resolution of the detector. Okay. So in some cases, you will be able to use this information, like timing kind of information. The another option is that suppose see this thing that this LLP decays here and it creates some charged particles. So if you can identify those charged particles, you can actually try to get this point which is called secondary vertex. And this is your standard model background. All these particles are coming from the primary vertex. Here you have a secondary vertex far from the primary vertex. If you can identify this point, then you should be able to like remove all the standard model backgrounds theoretically, right? But again, it's not fully true because you are searching for this kind of scenarios where you have a point and multiple particles are coming out. But there are other like instrumental backgrounds like this one. So suppose one hadron, that hadron hits some part of the detector and it produces secondary particles. So in that case, it will look like a secondary vertex. Or suppose you have like some charged particles, the charged tracks, and you have some kind of, because of the reconstructions, you have some kind of accidental crossing, and this point will look like a secondary vertex. So you really need to know the full material map in order to suppress all those backgrounds. And even this material veto map is not enough. You have to apply some cuts, like the invariant mass of the vertex and the track multiplicity. If the number of tracks is high and if the invariant mass is high, then you can reject all those backgrounds. But if the mass of this LLP is small and if the number of particles coming from the secondary vertex is small, then it's actually very challenging. Okay. And this kind of situation is very difficult to study in case of, say, at LHC, unless it decays to muons. So in such cases, like you have light LLPs, and which decays to say E plus E minus, and the mass is say 1 GeV. In such cases, you can use different like dedicated detectors like phasor, which is actually this LLPs can get longitudinal boost from the decay of mesons, and we already have one detector in place called phasor detector, which is 480 meter from the primary vertex. So that can be sensitive to this kind of light long-lived particles below 1 GeV. Okay. And you can also think of some kind of fixed target or beam down experiment, which are also sensitive. Okay. And if you have like transverse detector, it can actually complement CMS results. And one such detector is called Mathusla, which is a proposed transverse detector. So like you need multiple dedicated detectors to identify various signatures of LLPs. And I'll just talk about only one, in last 1 minute, I'll just talk about one point, which is actually the following, that LHC is not built for long-lived particles because they actually thought that new physics would be prompt. So then now actually they are modifying their techniques and all these things, but initially it was not built for long-lived particles. But for future colliders, we have this option, right? So we can think ahead and we can design the future colliders in such a way that you have a place for dedicated detectors. Okay, so we have done some analysis. We have actually done some work in this direction. We actually proposed two detectors, one in the transverse detector and another one is the forward direction. So we are actually working in this direction, and actually there are actually many things to do in that for future colliders, and I just want to thank my collaborators like two students, Ritoja and Prabhat, who have actually done work in this direction extensively. And we actually try to analyze a few things like the dedicated trigger developments for long-lived particles using like timing variables and energy deposition, muon spectrometer. We are actually trying to explore various options, and we also use machine learning in order to see this kind of strange signatures. Okay, so this is the summary. So for LLPs actually are really motivated, well-motivated theory, and you can find it in many BSM scenarios. Signature not only depends on the decay products, but also depends where it decays, the lifetime. And many unusual signatures are possible, and you need like some kind of good knowledge of detector in order to estimate the backgrounds. And you need dedicated detectors to probe light LLPs. And I think for future colliders, we should think about dedicated detectors so that we can we can cover all the possibilities. Okay, thank you.
Questions?
I just have a very naive thing to ask. In your time analysis, that slide which you are showing about the timing, how do you know how long you should keep this time open, the gate open, let's say, once you have, what motivates that? Yeah, here, let's say.
Yeah.
What motivates to keep that, how long you should keep that open?
Okay, so I think they actually apply some cut of around 20 nanosecond. Okay. So if the LLP reaches after that.
So you're expecting that your LLPs will be all within that.
Yes,
20.
yes.
There are these exotic candidates in the charm and the bottom regime, where theoretically there are many predictions for long-lived states, bound states. as per strong interaction, bound states as per strong interaction. So they can only decay weakly or otherwise.
Okay.
So these kind of signatures in the tail can we also apply for such states? And also, if you say that dedicated experiments are needed for such states, we need dedicated experiments for each of such states. It actually is varied over 3 to some 10 GeV.
So
Thank
it depends on the, okay, so it depends on the lifetime and the decay product of those particles. So if you specify those things, then like, yeah.
Yeah. So there is this tetraquark BC UD, U
Okay.
bar D bar,
Okay.
which we claim that will be like 40 MeV bound, for example.
Okay.
And it can decay only weakly.
Okay. So the point is that if it decays within some, the problem is that what would be the background and what's the decay product? If it decays to muons or something, if you have like muons, I think we'll be able to, I think we can ask Kajoridi also, like, because you are also doing this kind of analysis, right? B2S gamma or so for, if you have muons, I think you have a chance. And if it is like only some hadrons, and if it is displaced by a few millimeter or something, then I think it would be very difficult. That's what I guess. But one can study actually.
When we put out this paper, we communicated with some people in LHC, Vanya Balev.
Okay.
I don't know that. I don't know how to pronounce the name.
Mm-hmm.
So they said it will be really hard to actually detect it, at least in LSC.
Mm-hmm. But we can discuss actually. I can see
sure.
that paper and I can actually try to understand.
Okay, I forgot to ask if there are any questions on YouTube so that someone can tell. Oh, okay, then I think we can go for coffee. What time we should assemble? 11:45? Yeah, let's thank all the speakers. And the mass splittings and the mixing angles are measured. So now this is the evidence that, there is physics beyond the standard model, because the standard model does not include the neutrino mass. And the oscillation experiment measures the mass square differences and the mixing angles. And the limit on sum of neutrino masses come from cosmology. So the three neutrino paradigm is very well established. It is characterized by three mixing angles, theta 2, 3, theta 1, 3, and theta 1, 2, one phase. Like in oscillation, there is one phase. There are two other Majorana phases which do not show up in the oscillation. And all these parameters have been measured from the solar reactor atmospheric long baseline data. And we know that, there are this mass square difference. One mass square difference is 10 to the minus 5 eV square, and one mass square difference is 10 to the minus 3 eV square. So this is the atmospheric mass square difference. This is the solar mass square difference. We don't yet know that whether these two states are below this state or above this state. So this is called two different orderings, normal mass ordering and inverted mass ordering. We also know the mixing angles, like theta 2, 3, best fit is 42 degree, theta 1, 2, 33, and theta 1, 3 is less, 9 degree. And actually we know many of these angles with some amount of precision, but we don't know the ordering yet. The delta CP has a large uncertainty, and this theta 2, 3 can also be less than 45 or greater than 45. But apart from these parameters, the other parameters are measured with quite a good precision. However, there is one of the burning questions at this time, that are there more than 3 neutrinos, and there are reasons to believe that if there is, then this is sterile, which means that this has no standard model interaction, but it can mix with the standard model neutrinos. And the question is whether they are light or heavy. And as I showed you in the title slide, that there can be, the sterile neutrinos are postulated at all energy scales. For instance, when we give small neutrino mass, then seesaw mechanism that needs introduction of right-handed sterile neutrinos, and it can give rise to the leptogenesis, which can explain the baryon asymmetry. There are also many low-scale seesaw models, and we have KV scale sterile neutrino dark matter in meson decays people have studied. However, most of these are theoretical postulations, and there are no really any hint. We just study the implications. However, there are some hints for these EV scale sterile neutrinos, and most of my talk I will cover these light sterile neutrinos. So this hint came in 1995. The first hint in favor of a sterile neutrino came in 1995. I was a PhD student at that time, and the LSND detector in Los Alamos declared their first result, and they found that there was an excess in the they were studying nu mu nu e oscillation, like nu mu bar to nu e bar, and what they found was that there is a 3.8 sigma excess of the electron antineutrinos, and the baseline for this experiment was about 30 meter, and they have the energy, pion energy, the neutrino energy was in the range of 20 to 200 MeV. So this was an accelerator experiment with these pions at rest, and then so this could be explained, this nu mu bar, nu e bar could be explained by oscillations with a delta m square greater than 0.2 eV square. Now, this led to a problem because the solar delta m square, solar was about 10 to the minus 5 eV square in the ballpark, and delta m square atmospheric around 10 to the minus 3 eV square. Now, in 1995, these things were not so well established. However, we already knew that this is the idea, and then if I have this solar here, and if my atmospheric here, and I need another independent mass square difference, then I need at least one more neutrino, and because it's around eV square, then this has to be sterile, that is devoid of any standard model interaction, because the constraints from Z decay
implies that there cannot be neutrino with standard model interactions below mz/2, that is below about 45 GeV. So that's how the sterile neutrino hypothesis got some, although it was there for the seesaw models, etc., for a long time, all these were studied, but experimental indication of a low mass sterile neutrino first came in 1995. Now, then another experiment, mini boon, was designed because I will explain later, although LSND had the observation of a nu bar oscillation, there are certain other experiments which did not observe any signal in the LSND parameter range. So that created some confusion that whether this is a real signal or there are some background effects. So it was decided to perform the mini boon experiment, which will study both this nu bar oscillation. It had a different L, like as compared to LSND. It has a different E, but it has the same L by E as LSND. And the oscillation effects are, at least for such small distances, mainly go as L by E. So if they have the L by E, same L by E, then they can probe the same parameter space. And this mini boon experiment declared their results, and then this is a result from 2018. And then here the mini boon showed that there is this excess of electron and the NUI and NUI bar events in their data. So mini boon sort of confirmed the LSND signal. Now there could be different scenarios to explain this. If we add a sterile neutrino in the picture, one was 2 plus 2, in which we have a sterile neutrino either with the atmospheric or with the solar. However, this was disfavored by solar and atmospheric neutrino data because solar and atmospheric neutrino data they do not support a dominant oscillation to sterile neutrinos. So what survived was this 3 plus 1, and where I have these 3 neutrinos, the 3 standard neutrinos and 1 sterile neutrino above. However, this 3 plus 1 scheme subsequently faced some strong tension. But before that, I will just show you this LSND and mini boon. If we combine, then there is a combined significance of 6 sigma. And if they do a 2 neutrino fit, then this blue shaded region is LSND, and this is the mini boon region. So you can see that mini boon plus LSND are sort of consistent with each other. So if we go to the 3, so this was done in a 2 neutrino fit effective. So like you assume there is only nu s kind, like nu e, but you do an effective 2 neutrino analysis. However, in general, we have to go to a 4 neutrino framework where I have to extend I showed you the 3 cross 3 U matrix. We have to extend it. We have to have extra mixing angles and phases. So, however, what was the tension is mainly between the disappearance and appearance tension. And these are short baseline experiments. So the solar and the atmospheric oscillations actually, they don't contribute because they average out. So then what happens is here I have this, so different experiments were carried out. Like this is the appearance experiment, mini boon and LSND, where we have a nu mu going to a nu e or a nu mu bar going to a nu e bar. However, there were some nu mu bar disappearance experiments like this CDHS. This was an earlier experiment, accelerator based. Then Minas also gave this blue. So they did not observe anything. And Pratik mentioned about ice cube atmospheric. So this is also the region from the ice cube atmospheric. And by these plots, we mean that because they have not observed any oscillation, these regions are ruled out and this 0, 0 is allowed. So they are consistent with this extra mass square difference and extra mixing angle to be 0. So they rule out this position, this part. However, LSND mini boon will allow like these kind of regions. So there is a strong tension between the appearance and disappearance result which comes in the feed. There is another thing which was puzzling in the mini boom, which is that they observed excess events in the low energy beams above background. So this is like their background electron neutrinos, and this is the photon background, and there are a lot of discussion as to what is the cause of this. And so they are detecting these Cherenkov rings. However, the main thing in mini-boon is they cannot differentiate between the Cherenkov cone of electron and the single photon. So the electron excess that they are seeing, can it come from the photon? But whatever single photons they saw from NC background could not explain this excess. Also, if we do this 3 plus n sterile neutrino scenario, then that can also not explain the mini-boon low energy excess. So there were lots of BSM physics which is studied to explain this. And this is the experiment which is coming up in Fermilab, the short baseline neutrino experiment, in which microboon has already given result. There is some neutrino even detected in SBND. So these are liquid argon based detector, short baseline neutrino detector. And so there are these detectors at 3 different distances. So they can measure the probabilities at 3 different points. And by comparing them, they can say if there is EV square oscillations or not. And different detectors have different purpose here. And the microboon experiment is a liquid argon TPC detector which has started taking data since 2015, and their primary goal is to identify if the mini-boon low energy excess is due to the background or some sterile neutrino and electron neutrino. They, since liquid argon detectors have excellent resolution, they can separate between electrons and photons. So microboon gave their result in I think 2021, and they disfavored first of all this delta 2 gamma as a origin of this low energy excess, and then they did not find any electron neutrino excess in the data. So this is the microboon result, and this is the prediction with no low energy excess, and this red is with low energy excess. So they are consistent with this. However, there are some discussion that the electron neutrino excess cannot be excluded in a model independent way. So they have used some models, and so also if this low energy excess still persists between LSND what mini-boon observed, then there can be some new physics, and I think the results from HBN will be somewhat conclusive. If I do the mini-boon and micro-boon combined fit that people have done, and then what one sees is that, it's still between mini-boon and micro-boon combined fit, the 3+1 regions are allowed. However, the main tension is between the disappearance and appearance data. So then the question is that we considered EV scale sterile neutrinos, whether we can have lighter sterile neutrinos. And there are some indirect motivation for such cases. For instance, this is the T2K and NOVA data for the delta CP determination, and this is normal hierarchy, and this is the T2K based fit, and this is the NOVA based fit. So you can see that the T2K and NOVA based fit are not at the same place, and there is some tension between T2K and NOVA. So this is showing the same thing. This is the T2K based fit of delta CP, NOVA, and this is the T2K. And it was proposed in sorry, the reference is somehow gone. So it was proposed by Andre Diguvia and his collaborators that if they take a light sterile neutrino of mass say 10 to the minus 3 minus 2 EV square, then they can explain this because of these additional parameters. So this is the joint fit, and this is the T2K and NOVA fit. So they are like in the like nearby area. Another thing was this spectral upturn, which Basu mentioned yesterday, that in the solar neutrino data, this MSW effect predicts a spectral upturn, which is not seen. And people have proposed ultralight sterile neutrinos of mass 10 to the minus 5 EV square and sine square 2 theta also very small to explain this. So these are some of the motivations of the ultralight sterile neutrinos. So we studied that, Another thing which I did not mention, that the 3+1 scenario of a sterile neutrino, which I will discuss, is also seriously constrained from cosmology. But the question what we thought is that if we go to lower mass square difference, then whether such kind of things can be evaded. So if we take this, that if we allow lower mass square difference and if we allow all possible arrangements, then we can have 4 different arrangements, one in which the sterile neutrino is above in both cases and the 3 active states are below here, and the another one in which the sterile neutrino is below and the 3 active states are above, and the 3 active states can have normal ordering and inverted ordering, and here also the 3 active states can have normal ordering and inverted ordering. So this is the SNO scenario and this is the SIO scenario. So what we used was the mass variables. So by mass variables, so the oscillation experiment is telling us about the mass squared difference. However, we have the beta decay from which we can constrain this combination of mixing angle and mass squared difference, and there is a limit from Catherine on it. Then neutrinoless double beta decay, it constrains some other combination of the mass squared difference, the same combination but with the phases. In this, combination of U mixing matrix element and the masses, but with the phases. And of course, there is the cosmological mass of the light neutrinos that is also constrained. So what we tried to see is that how these different mass spectra are constrained from these scenarios. So for this, we took some allowed parameter from the experiments. We took 3 sample mass square difference, 10 to the minus 4 eV square, 0.0 eV square and 1.3 eV square, and we took most, whatever mixing angle is allowed, the highest value from that as the mixing angle. So then, first of all, we studied the effect on cosmology. So in cosmology, what happens is the neutrinos contribute to the radiation density. So that is the N effective is actually the energy density of the relativistic neutrinos. But if I have some other relativistic radiation, then that can be added to this. And then the N effective will include that SM value plus the delta N effective. So delta N effective is N effective minus N effective SM, and N effective SM is known. And this delta N effective can affect the Big Bang nucleosynthesis, large scale structures, cosmic microwave background, etc. So what happens if there are sterile neutrinos? Sterile neutrinos will, okay, thanks, contribute to N effective and the sum of neutrino masses, but the sum of neutrino masses now will have this MS effective, and this MS effective, depending on whether neutrinos are thermal or non-thermal, they have a different form. And so what we used was this from Planck, this result where they have given the N effective and sigma mi, including the N effective and this MS effective in their fit. So this is the sterile neutrino fit from Planck, where they have included this. And for massive neutrinos, I have 2 parameters. Like if I have massless neutrinos, then only N effective will do. But if I have massive neutrinos, then in the fit, I have to also include this. Now, if I have fully thermalized neutrinos, then this delta N effective will 1 because the active and sterile states are in equilibrium. So it's like N effective is 4. However, because the data says that N effective is like delta N effective 1 is disfavored from the data. So that means that, these are like non-thermal or partially thermal, in which case one can show from the energy density that the MS effective is related to this here N4 by multiplying by delta N effective. So when they are doing partially thermal, then they do a Fermi-Dirac distribution, they multiply it by delta N effective. So that's how they are relating the delta N effective to the partial thermalization. So what we did was we used this value and we used a delta N effective according to this value, and we tried to see what are the constraints we are getting for different spectra that we are considered with different masses. So this is the like these 4 different mass spectra, and this is the cosmological bound, and these 3 are for 1.3 eV square, 0.01, and then 10 to the minus 4 eV square. And this is the, so this is how the delta N effective comes in the cosmological mass bound. So what we see is that, here all the mass square difference are allowed for SNO-NO, and for the SNO-IO, where the sterile neutrino is above, but the three normal active neutrinos are inverted ordered, there I have this 0.01 is marginally disallowed, and 1.3 eV square is, disallowed. Sorry, this is not correct. 1.3 is marginally disallowed, but 0.01 and 10 to the minus 4 are sort of allowed. And here what I see is that 1.4, if I have SIO-IO, then or SIO-NO, 1.3 eV square and 0.01 eV square are disallowed by the cosmological bound, but the 10 to the minus 4 eV square is still allowed. So we also saw what are the constraints from beta decay, and here we have the Catherine limit, this one. And what we see is that for the SNO scenarios, this is fine. But for the SIO scenarios, even Catherine disfavors this 1.3 V square. So normally we say that it's disfavored from cosmology, but even the Catherine data also disfavored a 1.3 V square sterile neutrino, and mind it, we have considered this to be non-thermal. And then we did from the neutrino-less double beta decay. So for neutrino-less double beta decay, this is the 3 generation. These shaded regions, dark shaded regions are the 3 generation, and the light shaded regions are for 10 to the minus 4 eV square here, and 0.01 eV square and 1.3 eV square. So what we see is that SNO-NO, and this is the Kamland-Zen, which is the current bound. So we see that the SNO-NO is allowed for all the delta M square. But if I go to SNO-IO, then what I see is that the predictions are little higher, and the part of the parameter space are disfavored, like already ruled out by the Kamland-Zen, but part of it is allowed. So that is the thing we found for SNO-IO. And if I consider the case where the sterile neutrino is below, that is the inverted ordering for sterile neutrino and normal ordering for the neutrinos, then what we find is that 0.01 eV square is like part of it, a large part of it is disfavored by the Kamland-Zen data, and 1.3 eV square is completely disfavored. So even the neutrino-less double beta decay also disfavors this. So here, all these plots can be understood when we express this, we can express, so one here, the lightest mass square difference is my parameter, and I express all the other masses in terms of the lightest other, in terms of the known mass square differences. So, so in terms of that, this is my parameter, and the phases are varied here. So that explains the width, the phases and the oscillation parameters. So this is what I said, this is allowed, this is part disallowed, but this is completely disallowed. And then we also did for the SIO-IO, where both are inverted ordered. And here, depending on whether my delta M square sterile is greater than delta M square atmospheric or less than, I will have a, so this is my 10 to the minus 4 eV square. So I will have a, different scenarios. And what we, but if you can vary that, and this plot will cover all the scenarios. Again, we find 1.3 eV square is ruled out. The results are somewhat similar. Here we get slightly higher prediction, because the mixing angle that we chose for 10 to the minus 4 eV square is large. So this is the thing, that this is allowed, this is partly disallowed, and this is disallowed. So this is what we had seen for the mass spectrum in presence of a very light sterile neutrinos. And then I thought I will just mention, because I said sterile neutrinos occur on all energy scales and how they are very relevant for neutrino mass generation. And this is the type 1 seesaw, where we add a right-handed sterile neutrino. We have the Dirac mass and the Majorana mass, and then we can diagonalize this. So this comes from the dimension 5 Weinberg operator. And when we integrate out the heavy field, we will get this seesaw term, MD, MR inverse, MD transpose in the approximation that MR much greater than MD. And we can find the mixing angle by diagonalizing this. And this light heavy mixing goes as MD, MR inverse. And and this is the UPMNS, which is in general non-unitary. However, this, if MR is much large, then this correction is small. So this is how the sterile neutrinos help in heavy sterile neutrinos. And there are models which are like usual gut-based models consider these heavy sterile neutrinos as 10 to the 14 GeV, 16 GeV. However, there are also a lot of TeV scale models, especially when the LHC data came, then a lot of TeV scale models were considered for this, like the inverse seesaw, linear seesaw, etc. So all these inverse seesaw, linear seesaw models are like, they add extra neutrino. So some extra neutrino and they enlarge the mass matrix. And so I wanted to mention that, how to generate EV scale sterile neutrino. It's not very easy to have a EV scale sterile neutrino. And this is a seesaw based model proposed by these people, where they take one extra sterile neutrino. So earlier when I said this, then in general, this matrix is 9 cross 9 because I have 3 left-handed, 3 right-handed. And in this model, they said that 3 right-handed neutrino, but 1 extra singlet. So this model is 7 cross 7. And this can be diagonalized under the approximation MR is much greater than these Dirac terms. And then I get M nu, which is a little more complicated. And this also predicts my M4, which is the sterile neutrino mass and the light heavy mixing, because here it's a 2-step seesaw. There is a seesaw of the heavy neutrinos, which will give rise to, this spectrum, that 3 left-handed neutrinos and 1 sterile. And then there is another seesaw where the light heavy mixing between the sterile state and the light neutrino state is given by the sterile mixture, which is observed in the experiments. So this is one way. And then I was checking, and then I saw that Rajaji has worked on one paper where, they considered these extra dimension models to give to light sterile neutrinos. I thought it's interesting. I will take a look, but I was just searching and then I find it. So I thought it's a good point to mention this. So this is my summary, that sterile neutrinos can exist at all energy scales, but it's very difficult to, all are like sort of indirect signature. Then also it's very difficult to prove. There are some hints in favor of an EV scale sterile neutrino from oscillation experiment, but there is a strong statement tension in data. And they are also constrained from cosmology, beta decay and neutrino-less double beta decay. We explored the question whether the lighter than EV sterile neutrinos are allowed, and we considered 4 different mass spectra. And what we found was that constraints from cosmology and neutrino-less beta decay disfavor, they are more stronger than the Catherine constraint and disfavor some of these mass spectra. So I found this, so they are saying that the sterile neutrinos are $10, but I thought that if if by chance these LSND signals, etc., are confirmed by SBN, then that will be really a new direction. So it can be $1 million also. Thank you.
Very nice talk. So questions, comments?
The previous transparency that you had, the new S, that mass matrix.
Is it on?
Oh, can you hear me now?
Which one?
The previous one more. Here.
Yeah.
Why is the last entry 0, the new S?
So, like this is the structure which will give you the kind of phenomenology we need, but you can have models which will give you this as 0.
And
So
that would not fit well with the data. Is that what you're saying? Or?
Means I have not checked. If models, there are models where you can put this term. I have not checked whether that can what correction that will make to this. I think this with some zeros, the diagonalization is easier. So what these people did was they found this structure which will give you a M nu and a M4. And we also did some study, and they also did in based on, A4 symmetry, we have some models, and then we can justify this structure. But I don't know, like, there are models also where this is kept. Whether such models can give this, I have not checked it.
So you talked about the cosmological constraint. So if you take the recent DAISY BO data, so does it rule out some of the hierarchies, especially this SNO, NO, which is completely allowed?
We took this Planck data because the problem is that the most of the data is not giving you this, including the sterile neutrino in the fit. And then we cannot take the 3 generation. So the assumption goes in cosmology is 3 degenerate light neutrinos. But then I thought that we cannot use that because we have not done any, data fitting. What we have done is we have used their data, and we have taken different mass spectra which will relate this M1, M2, M3, M4, and then we have seen what happened. So what you are saying can be done, but it has to be done in the code. And then only we can say, I was thinking that Shobhik shared some post in Facebook that he has done some analysis with this DESI bio data, but I have to see if it is for sterile neutrino or active.
This is more a comment. There is a proposal, actually, Vivek Datar is looking into it and actually pushing to set up a detector near the Kudankulam reactor. Near the Kudankulam reactor.
Okay.
So second reactor is almost coming up.
Yes, yes.
There's a proposal for 6 reactors.
Okay, okay.
So the thermal power is quite high, and you have very good flux of neutrinos. So somewhat slightly higher mass range of steriles can be probed there because you will have only nu E bar. So you can look for unitarity violations. And if there is any, then you will see that there may be some evidence of sterile.
You mentioned this point because certain things I didn't mention because of time. There are lots of reactor data, DANS, NEOS, neutrino 4, which are saying higher delta M square.
Yeah.
And it will be very good if we can, because that situation I didn't mention because that is another field which is like not very clear what is the situation. But there are DANS, NEOS, neutrino 4, these 3 experiments, they are giving some hints of sterile neutrino at EV square, even 10 EV square.
That would be very good for
really
Kudankulam.
good to, yeah.
So
Another thing I didn't mention also the gallium anomaly,
Yeah.
which also can be like the reactor antineutrino anomaly is now gone, but the gallium anomaly can also be explained in terms of the
So this proposal is to set up a detector within the campus of this Kudankulam at a distance of few tens of meters.
A long time back, I discussed this with Uma Shankar, that whether we can have Uma Shankar, Mohanty, we discussed have a reactor facility here.
Yeah.
That is because before these things were coming up, long time back.
Yeah.
But I didn't know this. I will be very interested.
We should talk
to
to
know.
Vivek, and maybe there is more input, theoretical input that can be given to
yeah.
this. Yeah. But he has already talked to the people in Kudankulam.
Good.
I'll have this conversation here because we are running out of time. Any other comments, questions? Later you discuss. We are behind time. Okay. Sorry. Okay. Thanks, Shubha. Yes, we have to move. Thank you. Actually, there's lots more to discuss. I'll also discuss with you. We'll go to the next talk. Surface magnetic field of neutron stars by Subarti Ray, who's actually currently a visitor at IMSC, but we are all looking forward to the talk. So I'll give you a warning 5 minutes before.
Sure. Thanks. I can see that the crowd has diluted out. So anyway, thanks a lot for
to all of you for giving me an opportunity to talk, give a presentation here. I thank in particular Manjari Bakshi, who gave me this 1 month visit here to talk to his groups about pulsars, and they're really doing some good work up here. So last few years, I've been trying to do a few things on my whole life. I've been doing the strange stars and all. Then I looked at the GR solutions. At certain point of my time, I was also doing the modified gravity applied to the pulsars and the neutron stars. But basically, all of these things were tied to the neutron stars. Then of late, I moved on to looking at the emission of the pulsars, because that is one thing which connects the object up there to what we actually measure. And there has been a lot of new results from the observations which motivated me to look back to what is happening at the surface of the neutron stars or the pulsars, more so from the polar caps, where the beams are they have the seed in energy from the surface of the star at the polar cap. So this work is mostly done with my former PhD student who got her degree in this year, Kathleen Selig. Okay, so yeah, it's good to read from here. So the basic dynamics of a radio pulsar says that the magnetic field plays a big role in a neutron star, because all of the emissions that they eject, like which goes along a distance of a few kiloparsec to the maximum, I think it has an optical depth of 10 kiloparsec. So to throw matter to such a distance, one needs to have a very strong magnetic field at the surface of the star. So then, if you think of a dipolar magnetic field, because the beams come out in poles, so a natural choice for the magnetic field structure is to have a single dipole, and then the beams are ejected from both sides of the poles. So one of them which cuts the Earth, so we do measure them, and we make our models based on this. Now, when we think of dipolar structure, then we will have areas which call the closed field lines, and then we'll have the areas which are called the open field lines. The closed field lines are the areas where it is charge saturated, because the strong magnetic field leads to pair creation, and then it fills up the whole space with charge density. The density is called the Golding-Julian charge density. And the open field lines give are the one. Okay, to say it in this way, that the closed field lines has a boundary with the open field lines, where it is called the light cylinder, because a charged particle going along the field lines will go at the speed of light, but then the pulsar rotates. So at some point, the linear velocity of the pulsar of the charged particle is the same as the speed of light. So the charged particle is not bound to go along the field lines, and then it will become free. So it's free to choose any path. So that one, maybe I should go to the next picture and tell you. So this is what it looks like. So these are the closed field lines, and these places are called the open field lines because the linear velocity here is the speed of light, and hence the charged particles are not bound to travel along the field. So then what happens is that here at this surface right here, when the charged particles form, they lead to curvature radiation, which comes up to a point called the inner gap region. They're accelerated up there, where they form something called, so this leads to some coherent radiation, and that one forms the beam which shoots up a few kiloparsecs. So not all of the charged particles that form here do take part in forming the beam. It's only like a fraction of it, 10–12% of it shoots up as the beam, and the rest comes out as gas, because when someone really observes it closely, they see that there is a diffuse matter near the pole, a little bit away from the star. Right, so said so, let me go back. So the beam, beam is ejected relentlessly, meaning that it has to have a continuous supply of charged particles, and that is where it is suggested that the pair creation process takes place, and it takes place continuously. So it's something like this, that near the surface, it's a very strong magnetic field, and the pair creation creates the electron-positron pair, one which is selected by the type of field at the pole. It accelerates up, and the other one, the other part of the pair, actually hits down the hits down the surface. Hits down the surface, and it heats up the polar cap. So this is also has been modeled, and there are a lot of theories about it. So this is kind of what it really happens. Well, is thought to happen. And the rotation axis, it all depends on the type of the rotation, as like the angle with the rotation axis, that how far away the light cylinder is, or how close the light cylinder is. So now, to understand what the type of magnetic field is at the surface and what is the decay of the field there, so one has to go back to the neutron star structure. So a general understanding which we all know from like a lot of the talks here and in other places, that we do have something what's called the core, which we are not sure if it is a quark matter or a nuclear matter. It's an open question, but it has a density of around 10⁻15 grams per centimeter cube. And then we have the outer core, which is the nuclear matter. And then the thing which we are concerned with is the crustal matter, because this is the place where the conductivity of the matter, which is very essential for the magnetic field decay, is lower than what is in the core. So if we think that the core is of the nuclear matter, its conductivity shoots up. So then we are not able to hold any magnetic field there. So the magnetic field at the outer crust is actually most suitable to hold some the magnetic field. We are not sure where it is anchored in the neutron star. It's like a standard saying is that so we know that a magnetic field, if we have a very strong magnetic field at the core of a neutron star, then we will have a few problems. One of them is that since the nuclear matter is highly superconducting, then it can lead to Meissner effect, type 1 or type 2, where in a type 1 superconductor, the field lines are pushed out, and if it is type 2, then it forms bunches, but we won't have any dipolar field structure. So this is one problem, to have a body-centered dipole, and also to host the magnetic field, or to anchor the magnetic field within the star. So the other problem is that which comes from GR. It's not problem, it's a challenge that we cannot find a solution because the field, because the dipolar field is vectorial in nature, and it doesn't allow any interior solutions for a spherically symmetric body. If it is so, as the field becomes stronger and stronger, then it deforms away from the sphericity, and Birkhoff's theorem is violated. And also we will be having a lot of problems from other aspects, like then it should give gravity waves and so on and so forth. But also the other thing is that the GR solutions, like someone wow. Wow. So then Luciano Rezzola and his groups actually found out a solution for a spherically symmetric body from GR, but he found out that it is not viable for any realistic equation of states. So we do have problems from the magnetic field in inside a star. So what are the way out is that, okay, let me tell you. So what we thought that, okay, and it has also been in the literature that a lot of people tried to work out, how about hosting the magnetic field only at the crustal part. So we kind of took that approach. One can ask questions that, well, it's not the right approach. I know that it's not, but unless we find any way to anchor the magnetic field at the center of the star, this looks like a good option. Okay, then what we can come down to is the radio pulse observations. And with the recent observations, with all the fancy telescopes and good software analysis, and large dedicated teams to take part in them, like the one which is in PTA, which is like doing a lot of good work. So they found some of the features, like the pulsar timing array groups throughout the world found a lot of the features which hasn't been explained in the present. So a lot of these features haven't been explained. So a few of them are like the mode changing, the nulling. The mode changing and the nulling are it's almost the same. So a pulsar, when it gives a pulse, then the shape of the pulse can change quite a bit. So this, like, it's a kind of changing of the mode, and at some point of time it can become even zero. So that's called the nulling. And then there are the subpulse drift, means these subpulses that seem to drift away from their position and then afterwards come back to this. So these kind of things which has been observed. And also, last but not the least, are the microstructures. Like when we see a nice plot of the pulse profile, they do stack up a lot of the images, and then they do an integrated pulse profile, and this is what they call it noise that they gets smeared out. So basically all of these things point to us saying that there is something going on at the surface where we don't know what kind of thing is going on. So it may be a change in the magnetic field or a change in the way the beams are formed. We don't know correctly, or any other effect that can affect the beams to be not consistent to what we are used to, and this lead us to actually work on the surface magnetic field of a neutron star or a pulsar. Now, when we talk about the magnetic field through the crustal matter, so our very old equation is the induction equation, which we get from the Maxwell's equations, and this second term, this second term on the right hand side is because the Hall drift, so it's like the drifting motion, and it has a Hall current. But then this is effective only on the toroidal magnetic field part, so it basically moves around. So we cannot. So then this effect is not so relevant for us. So which we want to see how the magnetic field decay through the crust. So the first term is the ohmic diffusion, which is relevant for our study. Hence, this reduces to a simple form. And then one can see from a purely dipolar magnetic field with axial symmetry, we can take this vector potential and using a Stokes stream function, which we get it from the fluid dynamics. One can give a functional form of the potential. And then when you put this back into this equation, so we get a differential equation, which is a kind of a diffusion equation or kind of heat flow equation. Right, so here the sigma is the conductivity and x is a fraction of r by the capital R, which is the radius, and then that was done in a flat space-time geometry. So what we also did is, like, because a neutron star surface and the crustal matter is basically at a 3 Schwarzschild radius. So 3 Schwarzschild radius means a 10 kilometer star is approximately at a 3 Schwarzschild radius, which means that the gravitational potential at the Schwarzschild radius is infinite, but then it comes down to 3 Schwarzschild radius, it gets a 20% effect there. So it is non-negligible. The gravitational field is strong enough, so we can take it as a background Schwarzschild. The gravitational field is strong enough than the magnetic field, which means that the magnetic field is not going to affect the gravitational field, whereas the magnetic field is getting affected by the gravitational field. So then we take a background Schwarzschild for that reason. Makes life simple also, like when you work out the equations. And then after some manipulation, we find that the vector potential form in the phi direction can take this form, which is a little bit different from our flat space-time form. And from there, so this function g of RT, the functional form is just the same like the f of RT, which we had for the flat space-time. And then with that, we also find the diffusion equation, this kind. So then what we did, we have to solve it numerically. So then comes the important part, that what happens to the outer crust of the neutron star is there is a matter density which is changing very drastically. So we really don't the main challenge, well, so which means that the microphysics at each point change at each stage. So which affects the conductivity of the matter at each stage in the crustal matter density. So basically, and then the other problem comes in when we try to solve them numerically for 7 orders of magnitude, then the codes actually break up. I mean, we cannot have a standard way of the equation of state which we solve, and then we get the mass and all. So what happened is that a simple model was given by Urpin in 1979, which is like this. So one can find a relation density with the depth d. So r minus small r is the depth, and then one gives a form of the density which resembles the numerical work which has been done by Datta, Thampan, and Bhattacharya in 1995. So then the electrical conductivity which we can work out. So it should have 2 components. One is from the phonon scattering, and the other is from the impurity scattering. I think, yeah, no, this is fine. So this is the form for the phonon scattering, which is dependent on the on the temperature of the matter. And then when one works out the impurity scattering, which is more toward the surface of the, which is more toward the outer part of the crust. So it is dependent on what is called the impurity parameter, which is given of this form. So I mean, this is like a model, and most of the people like don't know what type of species are there and what should be the real value. So it is a standard practice that most of the people who did work on this field, they take a value from 0.1 to 0.001 and they compare the results. Yeah, so the final form of the conductivity looks like this. And if we then we can also write the sigma in terms of the density, which looks a little bit untidy, but this is the form which we can get. Numerical results, as we say that this is a very standard practice for doing a diffusion equation. One solves the Crank-Nicholson method. For us, we tried a little bit different because we were having problems with the Crank-Nicholson method, which is we use the finite differencing method called the method of lines, which is not too far away from the Crank-Nicholson, but has its own benefits. I should run a little bit quicker. So we also needed to take a sample equation of state. So we took one as the Wall-Lecker model, and the other is the Birth-Johnson model 5. This is like a placeholder. It really don't have to be this, but we just took 2 and just try to see what are the effects it bringing on the final final magnetic field at the surface. So also it has been found that a neutron star, when it's born, it's very hot, and then in the first few like first 100 years, it emits a lot of neutrinos and a lot of other particles, and they take away all of the energy, and then they cool down, and they cool down to a temperature of 10 to the power 5.5 to 10 to the power 5.2 degree Kelvin, and that remains pretty constant throughout its lifetime, which is about 10 to the power 8 years. So these are the few results. We just try to see, I mean, what are the effects of the Q and T on the conductivity of matter. They're not really so. Okay, this is how the inner edge of the outer crust, and this is the surface. So this is how the conductivity changes accordingly. And then we found out how the magnetic field along the outer crust, how it changes with time. So when it is quite new, it's quite strong. And then we see a decay, which is quite steadily going down. And see the curved space-time actually gives boost up the field a little bit than the flat space-time. So this is the one which is which we need to look at. This is at 100 years after its birth. So the magnetic field becomes, it decays by a very small amount till at the later stage, it decays quite drastically. We have shown for both the equation of states, and one is for flat and a curved space-time. So I'm not going to read out all these things, but it says that, okay, here is something. So then what we did is that we say that, okay, if this is the magnetic field, then if there is a radial oscillation in the field, then the core is more, it's incompressibility of the nuclear matter is much more than the surface, and crustal matter, what they call crust, it is not really a solid crust. I mean, it cannot be, because if you think of iron 56, then iron 56, its melting point is 1500 degree Kelvin. So, and we are talking about the surface temperature of 10 to the power 5 degree Kelvins of that order. So basically, what we think of crust should not be a really solid crust, but some kind of fluid molten iron, if it is so. So if you have any radial oscillation, then the crustal part will actually oscillate a little bit more than the core, and we can think of the radial oscillation coming from the breathing mode of oscillations. Can be also obtained from GR, but the GR numbers are from, they are just a perturbative term, which is on the nuclear forces. Anyway, the other thing is that the frequency of such fluctuations, they are found to be of the order of kilohertz from some of the old references where they worked out. So this is also good, because we have the subpulses and the microstructures in particular. So they all are in the kilohertz range. So here we see that what are the pulsations, how much maximum the field changes for a 2% change and the 4% change of the outer crust, a 0.2% and a 0.4%, which resembles to only a meter fluctuation and a 2-meter fluctuation in terms of the real numbers. So we did for two, and here is our final one, where we see that the fluctuations actually, we were quite thrilled to find out that the fluctuations actually go up in time. So this is what we found, that the delta B by B naught, as it grows with time, which means that, which means that it is quite this thing that in observational data, it has been reported. I mean, it was reported before also, but this group formed like they conducted a study of 1198 pulsars from the 1000 pulsar array program on the Meerkat, and they found that there is actually the substructures and the subpulse drifting. They are more active in the old pulsars, means that if you take the fluctuations to be growing as they become old, then this seems to be, our approach seems to be quite a nice one, I should say. But pros and cons are that the pros is that it is able to show some direction that the fluctuations are growing. Cons is that the fluctuations are still too small. So we are trying now to better the results. A lot of things can be done to better the results. So things are in the pipeline. So we'll try to work out on them. I think I haven't shot too much in time. So a few of the selected references. And thank you for your attention. And just to note that if you want to know where this place is, the background picture is, it is taken by me in 2009 in a place called, it's a place called Drakensberg Mountains. And this is, so the real picture is this one. Thank you very much.
Thank you for a really very interesting talk. Yeah.
You at the beginning mentioned that the core can be superconducting, but the core of the neutron star, but that assumes that you have a quark matter in the core. Having purely hadronic matter cannot give you a superconducting.
Why? Because you will have a 10% proton is all there. See, I mean, you really cannot have a neutron matter, just purely neutron. It has to bind, right? So it has to be, so at any given time, snapshot in time, you will have a few free protons. And if you think of the big number, 10 to the power 57 baryons, we did something long back about charged stars. So like 10 to the power 18 protons, free protons in that big number can give you a huge charge, right? So
you're additionally taking the beta equilibrium into account.
Yeah, it has to take place, right? Else you won't be able to bind them, and then it won't be stable because the neutron decay time is quick, right? So in order to make it stable, you will have to have a huge fraction of proton. Not huge, but it's still quite big number.
Any other questions or comments? None? Okay, if not, let's. Oh, sorry. Srihari, of course, has to have a question.
Oh, he is sorry. I mean, you asked me to give a talk in 5 minutes and show a lot of pictures, but I mean, it'll be on the scope of this talk.
So the temperature that you showed, 10 to the 5.2.
Yeah.
To 5.4. Is it really that narrow band?
It's like we haven't solved this, but we checked a lot of the works which they have done. They actually narrowed down, and it's not just only one work. It's like a whole lot of people, whole lot of groups work them out. They're also they are model dependent, so I really cannot confirm. We took their numbers for granted, but of course, I mean, one of them is Rodrigo, then Fridolin. They did it it's like 12 years 12, 13 years back. I think Pons also did something like that. So we checked that a few groups actually gave these numbers. So it's like, but no, it is much more than that. What all of them said that it's not going to die change a lot. So the first stage is that it cools down quite drastically, and then it slows down, and then in this range. So it can change by like even if it changed by one factor, say 10 to the power 4, it's still larger than the melting point of iron. So you still get a molten matter at the crust, outer crust.
Okay. So let us thank the speaker again. And we go on to positivity bounds on HEFT operators by Shushoban Chattopadhyay. Shushoban, I will give you a 5-minute warning.
Point. Yeah, so good afternoon, everyone. First of all, I would like to thank the organizers for giving me this opportunity to present our work in this conference. Today, I'm going to talk about an ongoing work that I'm doing with Dev Shubro, who is a fellow graduate student like me at TIFR, and my co-advisor Rick. And so in this work, we tried to take the first steps towards building the Heft hedron, and we will see what it means as the talk progresses. Whenever we have a separation of energy scales, we can write down effective theories that are valid at a given energy scales and cares only about the relevant degrees of freedom at that energy scale. And there is obviously a cutoff of energy scale for the EFT, but the parameters of the high energy UV theory can be matched with the low energy EFT. But in this talk, I am trying to address a reverse question, that whether for every point in the parameter space of the EFT, there exists a quote unquote reasonable UV completion or not. So I will make it more precise what I mean by reasonable UV completions later. So for the purpose of this talk, this low energy EFT would be the Higgs effective field theory or the Heft, and the high energy theory would be some beyond standard model theory. So when we try to describe the physics beyond the standard model, there are two complementary approaches. One is the Heft or the Higgs effective field theory, and the other is the SMEFT or the standard model effective field theory. The main difference between these two is that in Heft, the Higgs degree of freedom is non-linearly realized, just very similar like the chiral perturbation theory, and Heft thus is also commonly known as the electric chiral Lagrangian. On the other hand, SMEFT, the Higgs degree of freedom is linearly realized, and so it's an SE2L doublet, as in the case of standard model. When we have a SMEFT, we can obviously go back to Heft, because as you can imagine, we can always expand the Higgs doublet in terms of the wave and the physical Higgs field. But the reverse may not be always possible. For example, if we have some EV theory generating a potential term like this, we can always make an expansion in the powers of the physical Higgs field, and which is a perfectly valid Heft expansion. But when I try to express it in terms of the Higgs doublet fields, I find it's some h dagger h raised to some fractional power which can never appear in SMEFT. There is another layer of subtlety here, that even if we can express the Heft operators in terms of the SMEFT ones, there exists some correlations among the when expressed as SMEFT. So for example, in when the vector boson couples to two leptons, we can write these 4 couplings in the most general case, and all these 4 appear independently at Heft. But in SMEFT, what we find is there exists a correlation among them when we truncate SMEFT to dimension 6. So only 3 of the coefficients here are independent when written in dimensions up to dimension 6 SMEFT. So the main point I want to highlight here is that SMEFT is just a subset of Heft, and there exist UV theories which do not map to this MEF space, but map actually to this Heft minus MEF space. And so we can always go back from Heft to SMEF, from SMEF to Heft, but the reverse may not be possible. And there exist correlations between the coefficients when written in terms of SMEF. And this thing that I am pointing out has been shown in all these references very rigorously using the properties of analyticity and some geometric properties. So this motivates us to look into the Heft operators. So if we try to construct vertices which comprise of only longitudinal gauge bosons and the Higgs field, we find that we can construct 5 such vertices like 4 V's, 3 V's, 1H, 2V, 2H, etc. So there are 5 different types of vertices, and in total there are 5 plus 4 plus 4 plus 1 plus 1. So 15 Heft operators contributing to these 5 different types of 4-point functions. Right. So when I try to list them down in terms of the Higgs degrees of freedom, I have this list of 15 operators contributing to the 5 different vertices. Each block denotes the operators contributing to a given vertex as shown. So for example, if we take the first block, this can be this only contains the Goldstones and the derivatives of them. So this can be related to something popularly known as the anomalous quartic gauge couplings or the AQGCs. So there are 5 AQGCs as you can see, and all these 5 can be has a one-to-one map to these 5 independent Heft operators. But if someone tries to write down in terms of SMEF truncated to dimension 8, what one finds is that there are only 3 SMEF operators, independent SMEF operators, contributing to these AQGCs, and so there exist 2 correlations among them. So, so if somehow we can find bounds on these 5 Heft operators, we actually can find bounds on these AQGC operators. And if for example we want to get to the SMEF bounds, we can use these 2 correlations to always translate those bounds to the SMEF. But as you can imagine, the reverse is not possible. Like if someone handed me the SMEF bounds, I cannot go back to the Heft bounds, because Heft is a more general EFT than SMEF. Okay, so now I will define what I meant by reasonable UV completions. So by reasonable UV completions, I meant UV completions that satisfy these 4 properties of Poincare invariance, causality, unitarity, and locality. So Poincare invariance and avoiding superluminarity leads to micro-causality, that the commutator of 2 operators outside the light cone should vanish. And for micro-causality via LSZ reduction, we can get the entire analytic structure of the correlators in the complex S plane. And once we know this analytic structure, we can use the properties of unitarity and locality to get some conditions which are known as positivity bounds that I will show in the next slide. So let's say I have a elastic scattering of 2 scalars, chi I chi j to chi I chi j. Then this amplitude has the following analytic structure in the complex S plane. So we have poles and branch cuts along the real S line, but otherwise it's analytic everywhere. So we can take a point, let's say S star in the upper half plane, and draw small contour around it C1, and then by use of residue theorem, we get this equation. Now we can deform this contour C1 to this big contour C2, which has an arc at infinity, let's say, and then try to see what happens. And so after I deform C1 to C2, I will get contributions from this the discontinuities across the branch cut. And then if I take the double derivative of this amplitude, and then what we find is that d2m ds2 only depends upon the integral over the discontinuities across these 2 branch cuts, and the contribution from the arc at infinity vanishes due to the popular Froissart-Martin bound that amplitudes can't grow faster than S square at high energies. So now we can use the optical theorem to relate these discontinuities to the total cross section of this process, and so d2m ds2 is now some integral over the cross section, which is always positive, and this gives us our master equation, the d2m ds2 in the forward scattering limit for elastic processes has to be greater than 0. So this is the equation that I will use throughout in the next few slides. So now we are in a position to answer the question that we started with, that the for UV theory satisfying these 4 properties, those theories do not span the entire EFT parameter space, but spans only a small region, this green region of this EFT parameter space. And the region that it spans should satisfy this positivity criteria, that D2M DS2 is greater than 0. So we can expand the amplitude in terms of the Wilson coefficient Ci's and the Mandelstam variables, substitute it back in this positivity criteria, and get the bounds on these Ci's, the Wilson coefficients of for the EFT. So till now I have only talked about the positivity of 2-2 scattering processes, but this 2 particle in states and the 2 particle out states that we have can be actually linear superpositions of the physical states of our theory. So we can make linear superpositions of the Goldstones and the Higgs to form the 2 in states and the out states. And when one considers this situation, it's not very hard to show that this whole matrix D2M DS2 for different combinations of in state to different combinations of out state, this matrix has to be positive definite for all these amplitudes to satisfy the previous positivity condition. So now these superpositions naturally give stronger constraints than the individual amplitudes condition that I have shown. So now we will try to construct this matrix for the 15 Heft operators that we have. And so each row here denotes a possible combination of the 2 particle in state. Each column here denotes a possible combination of the 2 particle out state, as you can see. And there are different blocks contributing to the different processes like V4, V square, V cube H, V square, A square, etc. Now, it's important to note that if we only consider the first block, then the bounds that we would get are weaker bounds as compared to the bounds that we would get by imposing the positive definiteness of the whole matrix. The simple reason being, by considering this submatrix, we are actually restricting our allowed superpositions of the in and out states. And also, as you see, this matrix is not block diagonal, so imposing positive definiteness of this matrix actually mixes up coefficients in the 2 different sectors. So measuring the Wilson coefficients in some sector like V square, H square can actually put constraints on the coefficients of V power 4 by using R positivity bounds. So once we impose the positive definiteness of this matrix, we can find out all these eigenvalues in terms of the Wilson coefficients and make them all positive to find the bounds on these Wilson coefficients. So for the V4 case, as I have shown, we have so I had shown that there for the V4 processes, we have 5 independent Heft operators. So now we have a 5-dimensional space, and here I have plotted the various projections in different planes of the Wilson coefficients. This magenta region denotes the experimental bounds that was obtained in these vector boson scattering processes recently, and and the green region is the region that satisfies our positivity bounds. That this green region is the one which has reasonable UV completions. So only the intersection between the magenta and the green region is the region that is within experimental bounds and can have reasonable UV completion. Yeah. Right. So in this way, as you can see, that we could reduce the allowed parameter space, and if one estimates it, one find that we could exclude more than 92% of the 5-dimensional volume, and only there is a very small fraction, less than 8% of this is within our what we call the 5-dimensional polyhedron or the heftedron that I was talking about. So for the SMIFT case, as we have only a 3-dimensional volume, and which is for the SMIFT, it's a 3-dimensional surface within this 5-dimensional heftedron. And so we could this was done in this paper, but using this, our bounds contain more information, and by using the correlations we can always reproduce this SMIFT result, but the reverse is not possible, right? So for the V square H square case, there are no experimental bounds yet, but still we could derive our positivity bounds. Now it's a 4-dimensional volume because we have 4 Wilson coefficients, and these are the various projections. Here I have used the naive perturbative unitary limits of 16 pi square, and this is what we get. So these are the key takeaways, that SMIFT is a subset of Heft, And we can always go back from Hef to SMEF, but the reverse is not always possible. And there exist correlations when SMEF is truncated to a given order or dimension. The SMEF operators, there are 15 of them contributing to the longitudinal vector bosons and the Higgs couplings. There are 5 different vertices that we can construct, and by the reasonable assumptions on the UV completions, we can derive some positivity bounds which significantly reduce the allowed EFT parameter space. For example, for the V4 case, we find more than 92% of the experimental parameters space does not actually have a reasonable UV completion. And for the V square A square case, there are no experimental bounds yet, but we could still obtain R positivity bounds. Thank you very much.
Thank you for keeping to time. Yeah.
Your this Mandelstam variable relations.
Yeah.
There was this M square thing, right? So this is probably related to the mass of the particles that are scattering, probably the scalar and the Higgs, right?
Yeah.
And
talking about this
there was this M square. Some 18. Yeah, here.
Right.
So
this U can be always expressed. Yeah.
This mass of the Higgs or scalar.
Right. Right.
Are they same? The mass of Higgs and
Higgs
scalar.
mass we can take the MH, and so here the
because if they are not the same, then it's not 4m square. It's 2m1 square plus 2m2 square.
Okay. That
now,
becomes up here.
My question is actually the real question is actually, let's say if you consider also some long range interaction. I'm asking based on some different system in my mind.
Okay.
But if you have some long range interaction due to some lighter particle exchange, this can introduce some additional cuts in your amplitude,
right?
Which can complicate the situation, right? Do you encounter such problems in your?
Here we only consider UV completions, and so we only the short rate.
So you only consider the unitary cut and some S equal to 0 cut towards the left hand side, or what?
Right. So this cut is the one.
Yeah, that's the unitary cut.
Yeah, no, this cut is not the. This is the multi-particle state. So we
have a 2-particle state, 4m square.
Yeah, 2-particle state. We have also 3-particle states, and all these branches, and this is due to the SU crossing.
Yeah, what I'm really asking is about this 3-particle cut. If you have a light particle exchange, which is actually off shell, then it can introduce some additional non-trivial cuts towards the left-hand side, which is typically called as left-hand cuts or some pion exchange cuts in hadron scattering, for example.
Right, that is.
Yeah.
Just one second.
Yeah, so these things you can subtract. You can, because you know the IR EFT, you can subtract this part, and so you can call the amplitude this. There's a singular IR part plus some M tilde, and all these bounds will apply on the M tilde, and the M tilde gets only contributions from the EFT, which is analytical polynomial in SNT. So that part you can, because we know what it is, we can subtract and use the same argument on the non-singular part, and we get this.
So if we know the cuts and the discontinuity exactly, we can subtract it. So it's
So in the end, it's a bound on the high energy. The masses of W it doesn't matter. So as you're right, that it should be MW squared or MH squared there. But in the end, you can subtract away this part, and the EFT contribution, you can apply this argument on that, and you still get this bound on the Wilson coefficient.
Yeah, thanks for the nice talk. I have a very naive question, basic question. So I've seen some of these things. Why don't people use, or maybe people have used, why don't people use leptonic operators using lep data to study these things? Because they mostly use.
We need operators that grow at least as E power 4, because D2M, DS2, otherwise it's not zero result. So for leptonic operators, if it grows, like people have done, like for dimension 8 SMEF operators, people have done. Yes. But dimension 6 we can't do for SMEF.
Very nice talk. Just a comment. I think this VVHH, this has constraints like from di-Higgs VVF production, it's called kappa 2V. I think there are constraints available. So, maybe worth checking.
Maybe I have missed the
constraints. Yeah, I think, they are there.
Once we get the constraints.
Very weak ones, but they're there.
Yeah. Right.
Thank you. Let us thank the speaker again. Come to the last talk of the session, exploring impact of extra dimensions on equation of state and structure of neutron stars by Debabrata Deb. I'll give a 5-minute warning.
Slideshow. Yeah. Hi, thank you. Thank you for this opportunity to present our work in this conference. So the work I'll going to present exploring the impact of extra dimensions on the equation of state of baronic matter and the structure of the neutron stars. So this work has been collaborated with Professor Manjari Bakshi from IMSC and Professor Shomista Bonik from BITS, Hyderabad. So let us start before jumping into what we have actually done. So let us discuss some how higher dimensionality actually come in the literature. So you can see there are many theoretical considerations that actually supports existence of extra spatial dimension. And other than that, there is string theory who are actually consider higher dimension like 10 or more dimensions, and later to solve other problems like gauge hierarchy problems. And so people are actually revisited the higher dimensional model to resolve it. And even there are some high energy, dark energy or dark matter model that actually supports the aspect of the higher dimensionality to explain those things. So it is exciting that recently in the gravitational wave direction of GW 170817, it has been observed that there is, so this is the only gravitational wave detection where the both gravitational wave and electromagnetic counterpart has been detected, and it has been found that the luminosity distance from the same event is actually different when you are observing from gravitational wave perspective and electromagnetic wave perspective, and you can actually see the error bar if you consider the higher error bar. So it is really high difference because it is in megaparsec thing. And later actually many theoretical paper actually came to study those things in the perspective of higher dimensionality, and they are actually trying to say that gravitational wave actually leaking into the higher dimensional aspects, and those why they are actually getting the low gravitational wave strain, and the calculation of that strain is not through the calculation of the strain, the luminosity distance is not actually correct. So they actually came up with higher dimensionality in that picture. And later LIGO and like Varga also themselves also studied these things, and they showed in their paper that this aspect of higher dimensionality cannot be actually ruled out. So this thing is actually exciting for us. So being neutron star people, if neutron star is the best laboratory to study such natural phenomena, so we actually jumped into the picture and tried to see what higher dimensionality will affect how they will affect the neutron star, any structure or equation state or something. So who actually attended last day's Professor Ritam Mallik's lecture, they actually know what the neutron star. I am not going to repeat that, but I can tell you what is the MR curve. So if you have a neutron star, so from the Einstein field equation, if you consider spherical symmetric metric line element to define the interior space time, from there actually solving the Einstein field equation, you can get two kind of equation, that is mass balance equation and the force balance equations. So those are basically TOB equation, and solving them using the equation of state, which for this case we have actually considered density dependent equation of state model to signify the strong interaction inside the neutron star. You can actually get this mass radius curve. So if you know the mass, so mass you know from the observation or so, and you can actually predict the radius. So this that how actually mass radius equation helps you. So what we did in this work, we try to actually
study the Newton stand completely in the higher dimensional framework, and we try to construct the equation state where higher dimensionality, effect of higher dimensionality is there. So we took a density dependent equation state already there and try to construct it putting the effect of the higher dimensionality. And finally, once the model is there, we also try to test its physical acceptability and stability. So you can easily think like this. So we have a d-dimensional Einstein-Hilbert action. Then we go on to we have derived the d-dimensional Einstein field equation where Einstein constant is not known. Then use d-dimensional weak gravity limit to determine this Einstein constant. Then use d-dimensional spherically symmetric line element for interior space-time. Evaluated the vacuum solution for exterior solution for the d-dimensional space-time. Then we have come up with the mass balance equation and the force balance equation, that is the TOV equation. Then we have extended the density dependent model for the d-dimensional space-time, and finally we achieved the mass radius relation here. Once we have achieved, so we try to test its physical validity with the modified Boosdal limit, which is applicable for d-dimension equation. And finally, we have tested the model if it is stable against the radial pulsation in the d-dimensional case. So it seems like life is pretty easy if you follow these steps, but it actually no. So why no? Because you don't know the value of the gravitational constant in d dimension, and or either way you don't know what is the value of Planck length. So there we actually following this Zwickbach's this very good book. Following that, we took this formalism. They have actually show there is a relation between the high dimensional gravitational constant, and so there is no point of considering that the gravitational constant is same throughout the high dimensional spaces. So following their work, we actually took this formalism where LC is the length of the extra compact dimension, and it depends on the different dimension based on this power d-4. So as I said, we took the Einstein-Hilbert action, then solved two Einstein field equation in equation number 2. Area of the unit sphere, you can see 3. Generally for the 4-dimensional case, it is 4 pi. For the other dimension, it will change. And we use the usual trace energy tensor for isotropic fluid we have considered here. Finally, you reached in the equation number 5, the Einstein field equation. So we have solved the exterior Schwarzschild spacetime metric for d-dimensional based on the vacuum solution. You can see the mass balance equation and force balance equation in the equation number 8, and this is the basically TOV equation, equation number 8. We did some scaling for our for convenience, and we have used the natural like we consider G 4-dimensional G is 1 and C is 1 for simplicity. So here we started like extending the effect of higher dimensionality on the like relativistic mean field, on the density dependent equation of state. So we have like 3 equation of field equation for the missions. So by considering the mean Lagrangian, using that solving the Euler-Lagrangian equation, we have this equation for the missions. Then we have equation for the baryonic equation of field equation and the leptonic field equation. Solving all those things, we can actually come into the equation number 19 and 20, where we have applied the relativistic mean field theory. And there I am actually showing in the equation number 18 a rearrangement term. So there actually all the G's are actually the coupling constant where Mason couples, Mason and baryon couples. So here, okay, one thing I need to say, here we have used sigma, omega and rho Mason. So iso-scalar sigma Mason, iso-scalar vector omega Mason, and iso-vector rho Masons. So solving all those field equation, we able to get the value of rho and p. And since here the coupling constant G's are not the constant, it is density dependent. We took the functional form given by Type et al. And used the respective this fitting parameters value, this A, B, C on those things from the Type et al.'s work. And using all this, we can actually come to the equation of states. So the extreme right side is left side is basically equation state for the different dimensional value, where we have actually computed this xi value. So we get trouble in computing xi value because any xi value actually not giving the solution of the TOV equation. So we get hard time to find for which like range or value we are actually getting the solution of the TOV equation and MR curve. So by that way this xi value is defined. So in the like middle and right end plot, you can actually see the how equation of state is actually changing with the changing of xi value. So one interesting thing in the Ritonda's talk, if you have seen the gravitational from the result of the gravitational wave, the bound they are giving for the 1.4 solar mass, they are actually favoring the softer equation state. However, the Neiser or Prex, they are actually preferring the stiffer equation state. So there is a dichotomy. So it is interesting to see. You can see that thing here also for the higher dimensional cases. For the lower dimensional, for the lower density, those are actually softer, but for the higher density, they are actually stiffer. So it is a interesting phenomena we found here. So we found finally the mass radius curve, although we have plotted all the MR curve for different dimension, but from the unit of the mass you can understand it is a apple to orange comparison, but for the posterity we have just shown in a same curve, same plot. So I'm going to say how we can actually compare. So here you can see for the 5 dimension and 6 dimension, we are actually when the xi value is increasing, the value of the mass is actually increasing. And you so question could be like this, why we are only showing 5 and 6, because beyond 6 we are not getting any maximum mass value. So that's why we limited our study up to 5 and 6 high dimensionality cases. So then we have tested the Bousdal limit for this, and this is the Bousdal limit for d-dimensional space-time, and we are way within that limit, and we can say that our solution is physically correct. Then it is important to test the stability of the model against the radial pulsation thing, and you can see that the fundamental modes are like greater than square of the fundamental frequency of the fundamental modes are greater than 0, which actually tells that our model is actually stable. So by the stability criteria, we have tested that our model is actually stable. And here we have shown some numerical value. You can see how the higher dimensionality we are getting actually the maximum mass. So here is the last column. It is now we have take the compactification, and so what is that? We are taking the projection of that mass in our 4th dimension. So you can see as the higher dimension is increasing, we can actually explain the higher mass neutron stars. So based on the recent detection of the higher massive neutron star, we can actually tell about those mass gap and so based on these higher dimensional theories. So and here all the density and pressures are also compactified. That means those are projected in the 4th dimension cases. So this is completely projected profile. Here we are showing those data. So what are the important takeaway? Important takeaway is we able to construct a Newton star model completely in high dimensional framework. We for the first time we able to show the effect of the higher dimensionality on the equation state. No other studies has been shown that, and we finally tested all those things like the physical acceptability of our model and the stability of the model we have checked. Now next in the coming few time we also try to check the observational signature of through our model, or try to constrain those based on the observational signatures. So that can be done in the next few years or so. So thank you, and thanks to Mr. Christopher Nolan, you can see the projection of the 5 dimension here. Yeah.
You are using the equation of state higher dimensions, right?
No, so yeah, so we are taking like equation of state density dependent there. So all the aspect where the space time is there, we like updated to the higher dimensional.
But then in the higher dimensions, you will have larger number of terms because you should have tensor particles and all. Because the tensor particle in 5D will be like a vector or pseudo vector in 4D. So
okay, so here our approach was the simplistic, as I say, sigma omega rho, that model. So those complexity.
But that is true in 4D.
Huh,
that
4D.
we know. But then in higher dimensions, there will be more because if you compactify,
Huh.
tensors in 5 dimension will become vectors, additional terms will come up.
Okay.
So do you take into account those extra terms in the 5 dimension or when you go to higher dimension?
So first we wanted whether means with this simple we can get at least anything stable in like we tried to do it very generic means D as a free parameter increasing the number. So in higher dimension means in the GR aspect we are not getting any stable. So with 5 and 6 we are with simple model we are getting some stable situation. Now we'll investigate more on the particle physics aspect that so what are the modification we need to do there. Yeah.
No, they should not be, but for whatever equation state we generally study, they are in the Minkowski space. Right. So yeah.
The extra dimensions are flat.
Yeah. For that way, yeah.
So what is the size of extra dimension you consider?
Okay. So we
Because
have
for one
also,
extra-
as I said, we have
so
not.
for one extra dimensions,
Ah.
it's excluded from solar system observations entirely.
Okay. What is that?
So it should be astronomical units that's excluded, one extra dimension in ADD model, Arcania.
So you are telling about the large extra dimensions, right?
You said it's flat, so it is large.
Yes.
You said they're flat, so they must be
So I am
large.
saying that whatever the equation state you are like deriving, all are in the laboratory frame. So that should be also in the Kerr space time, if you trying to say so. So these higher dimensions we are trying to say, those are Kerr space time, not flat space time. As a gravity perspective, those should not be like flat, because we are studying inside the higher dimension, like in Newton star.
No, but what is the size of the extra dimension?
That I am showing here. So from the xi, as I showed, you can see that xi is basically lower extra dimension. It is not the larger extra dimension. So xi thing. So xi is basically g d by g. And from the g you can go to the Planck length. So you can understand if it is 10 to the minus 15. So LC value is 10 to the power minus 15. So Planck length will be smaller compared to the 4-dimensional Planck length. So it is the smaller extra dimension, not the larger one. ADD model tells about that.
So there is a limit of micrometers for 2 extra dimensions.
So our will be less than that. And we are not considering it from the solution we are getting this. As I said, during the solution of the TUV equation, these kind of values are supporting the solution of the Newton star model. And whenever we are getting this solution, so this xi is basically gravitational constant in the 5 dimension by gravitational constant in the 4 dimension. And from the gravitational constant, you can actually link with the Planck length. And whenever you go to the Planck length, because the this 10 to the minus 15 value, it will be less compared to our Planck length value.
No, that I understand. Maybe we can talk later.
Sure.
One more question.
Yeah.
So you build a neutron star in 3+1 dimension.
3+1 spatial dimension.
No, 3 spatial plus 1 timeline.
In 4, yeah.
In 4. But then at what point of time do neutrons start probing extra dimension?
No, so
what density? I mean, they must all be related.
So it is not like based on any density. I am saying if higher density is there, it will be forever for there. We are not getting the signature. Like we are seeing everything in 4 dimension. Say there 5 or 6 dimension is there. There this study comes in because we are not getting those signature sitting in the 4 dimensions. So it is not density dependent thing, the higher dimension.
No, but you take bunch of neutrons, put more and more neutrons in a fixed volume, you will get a neutron star.
Yeah.
So at what point of time or how many particles you need to add such that neutrons pop into extra dimension?
No, I am looking not like that way. I'm saying that whenever initially you are starting, you are sitting in the higher dimension. Suddenly the higher dimension is not popping out.
At least for what?
Yes.
Hi. So when in the very first slide you showed some numbers in megaparsec.
Yeah. Yes.
Please comment on the errors on those numbers.
comment of the errors, like how these errors came?
So it's the first number, which is for the gravitational waves, is 40 plus 8 and minus 14. That's a very
Yes.
large range.
Yes, yes, yes.
The second one is plus 2.4 minus 2.4.
Yes.
So it seems as if the EM thing is completely within the error range
Mhm.
of the first one.
So those are calculated by like luminosity, all those things are calculated by those guys, like LIGO and Virgo guys. So I could not comment much about them, but I can clearly see that there is a difference in the luminosity distance, and then different studies actually showed that
the central rested values are different, but it seems as if the allowed range is quite yeah.
Yes.
Okay, yeah, thank you.
Okay.
Let us Thank you. Yeah. So we thanked everybody. And are there any announcements? At 3, after the talk, you can give it.